Good afternoon, everyone. We are Team Right Wing. I'm Karthik. We are here to present on dynamic stability and to answer the question, what effects does the center of mass have on dynamic stability of an aircraft? Just to set the stage, let's look at some basic definitions. It's there on the corner. So, we've seen the static stability refers to the initial tendency right after a disturbance, whereas dynamic stability is concerned with the behavior of the aircraft for a long period of time after the disturbance has been given. It can be seen that static stability is more of a precursor and a necessary condition, but not a sufficient enough condition for dynamic stability. We are concerned primarily with longitudinal dynamic stability. It is the stability along the pitch axis, that is the x-axis, moment along the x-axis. This is mostly influenced by the CG of the aircraft, which is equivalent to the center of mass. The example over here that of the variable that we're considering, or the parameter that we're considering, is the pitch angle represented by theta. It has two different parameters: the transient state and the steady state response. The transient state response is the behavior seen while the system is moving between two different equilibrium states, and the steady state response is the final state or the new equilibrium state the system achieves here. That is the aircraft here. The important point on the aircraft that is of concern here is the neutral point. It is a location where pitching moment is independent of angle of attack for the whole aircraft. Hence, we can say that the dynamic stability or the dynamic response here depends on the position of the CG relative to the neutral point. My teammates will continue.
Good afternoon, everyone. I am Tarishi. I'll be talking about the fixed CG case. This case is about isolating the mass effects without depending upon the shift in the CG positions. So, we are taking the case about increasing the weight, and the increased weight will be equally distributed on the aircraft. As you can see from the mass moment of inertia formula, I equals to mk square. For a constant radius of gyration, if we increase the mass, then the inertia increases. This results in two things. From the second equation, you can see m equals to I into acceleration. So for a constant aerodynamic restoring moment, as CG is fixed, so if I increases, the acceleration reduces. This leads to a sluggish response due to any disturbance or a gust, also due to for any pilot inputs. This also leads to the reduction in the natural frequency, as can be seen from the third formula and the graph. And yeah, my teammates will continue.
Now let's look into effect of forward CG on the overall stability. While concluding from previous presentations, we have seen for static stability, moving the center of gravity forward will increase the distance between the CG and the neutral point, hence increasing the static margin. And this will increase the longitudinal static stability. So when a wind gush attacks an aircraft, the aircraft's tendency to return to its original equilibrium position will be much higher, making the aircraft more sluggish as CG shifts forward. Now, considering the case of dynamic stability, the forward CG, we'll consider the case of short period mode, where short period mode is mostly involves angle of attack and pitch rate and not much of velocity as well as altitude. So, as discussed in the previous slide, forward CG will increase the restoring pitching moment, that is increase the pitch stiffness. So as a result, the natural frequency will increase as well as the damping ratio will also be increased, and this will cause the oscillations to die out fast, that is like decay faster. So yeah, that is the case of short period mode. And in case of phugoid mode or long period oscillations, it mainly involves the change between kinetic energy and potential energy, that is between the velocity and altitude. So here, when the CG shift forward, it will lead to a damping of amplitude, and hence the forward CG will slightly increase the damping. So so the effect of forward CG actually helps the both modes become more stable. So that is all for dynamic stability. Now coming to the effects of aft CG on dynamic stability. First, coming to longitudinal dynamic stability. In phugoid mode, since Karthik explained that for dynamic stability, it has to be statically stable. The aircraft has to be statically stable. But as CG moves rearward, the static margin decreases. That is, the distance between CG and neutral point decreases. So the pitching moment required for the aircraft to come back to trim condition is higher. We need higher restoring moment to come back to trim state, but we need higher restoring moment. But as CG moves rearward, the restoring moment decreases. So it's difficult to bring the aircraft back to the trim state as CG moves rearward. So this leads to a decrease in frequency of the phugoid mode, and the oscillation amplitude also decreases. As the CG moves rearward and it reaches near the neutral point, the oscillation ceases entirely. The motion becomes heavily sluggish. And as CG crosses the neutral point, it becomes pure divergence. It's impossible to bring back the aircraft to the trim condition. Any pitch disturbance results in unrecoverable exponential pitch away from the trim state. Now coming to the short period mode, as weight shifts rearward, the restoring aerodynamic force weakens. This lowers the undamped natural frequency of short period mode. As CG moves rearward, this shortens the moment arm to the tail, reducing the pitch damping derivatives. And as CG crosses the neutral point, the static margin becomes negative and the short period ceases to be an oscillation. It becomes purely divergent. As we can see that when the CG is forward of neutral point, the damping will be higher, but as soon as it moves rearward, the damping decreases, the frequency decreases and the amplitude decreases. And as it crosses the neutral point, it becomes purely divergent. Now coming to directional and lateral dynamic stability. As CG moves rearward, the static directional stability decreases and yaw damping also decreases. Thus, if disturbed, the aircraft will rotate to ever increasing angles of side slip, flying a curved path as shown in the figure that can rapidly lead to a loss of control. And the effect on Dutch roll, with aft CG, vertical tail movement decreases and yaw restoring movement decreases. It results in decrease in frequency, lower damping ratio, and it takes a longer time to settle. Coming to roll mode, the damping becomes weaker. The aircraft rolls more easily initially, but it takes longer time to settle. At last, coming to spiral mode, an aft CG weakens directional stability as explained earlier. Yaw restoring moment weakens and the spiral mode becomes more unstable. So this is what happens physically. Now moving forward with the mathematical derivations and expressions, which will be explained by my teammate.
Good afternoon, everyone. Now I will explain you how mathematically we can explain the stability of the dynamic modes. So far we have seen the theoretical explanation. Now we will look into the mathematical explanation. The fundamental equation used in the flight dynamics is the linearized state space equation of motion, which is defined as x dot equal to ax, where x is the disturbance variables, which is a vector, and a represents the system matrix containing the aerodynamic derivatives. For example, let us consider the disturbance vector as x equal to u, w, q, theta, beta. I'll explain the terms. U is the forward velocity disturbance, W is the vertical velocity disturbance, Q is the pitch rate, theta is the pitch angle, beta is the side slip angle, P is the roll rate, R is the yaw rate, and phi is the bank angle. Now let us assume the solution for x dot equal to ax as x naught into e to the power lambda t, where lambda represents the eigenvalues of the system matrix A. Now if you can see the characteristic equation, from there if we derive the eigenvalues, it will be appeared as lambda equal to sigma plus or minus I omega, where sigma represents the damping and omega represents the oscillation frequency. And we will see that in general, if we can see that if sigma is less than 0, oscillation decays and it is stable condition. If it is equal to 0, it is neutral. If it is greater than 0, oscillation grows, and it represents the unstable situation. And let us see, by depending upon the values of eigenvalues, how the different modes of equation was derived. If it is a complex pair, short period. If it is again complex pair, phugoid. Complex pair with the negative real value, Dutch roll. Real root all are positives, then spiral mode. Real roots all are negative, then it corresponds to the roll mode. Let us understand the important relationship between the CG and the dynamic modes of motion. That will be explained by the equation called momentum derivative m alpha, which is given as xcg minus xac into L alpha. Now, this derivative appears inside the A matrix. As if we change the position of the CG, this derivative changes, which affects the change in the system matrix A. As system matrix changes, eigenvalue changes. When eigenvalue changes, it affects the damping, oscillation, and again stability changes. That is the important connection between the CG position and the dynamic modes. Now let us look more in deep depth how each mode is varying in mathematical point of view. Now let us look at the phugoid motion. It is a slow acting long period oscillation which involves the interchange of kinetic energy and the potential energy with the significant variations in altitude as well as the airspeed, but relatively at constant angle of attack. Now if you can see, the mathematical model of the phugoid motion is given as v double dot g by v naught v dot plus g by v naught v. This is the second order differential equation where v represents the velocity disturbance, since one of the parameters that is continuously changing in phugoid motion is the velocity, and v naught is the steady flight velocity, g is the gravitational acceleration, and natural frequency is approximately equal to the factor g by root over g by v naught. Now this zeta is the damping factor that will determine the stability of the phugoid motion. If it is greater than 0, oscillation decays and it comes to the stable condition. If it is equal to 0, neutrally stable, and parallelly if it is less than 0, oscillation grows and unstable condition. Now if we move to the short period oscillation, which is a rapid and heavily damped pitching motion about the aircraft center of gravity, which will last longer between 5 to 10 seconds, and the mathematical model that will be determining a short period oscillation. Like if we compare the equation with the spring mass damper system, we can come to end like an equation like this. So where alpha determines the angle of attack, zeta represents the damping ratio, omega represents the natural frequency. Again, depending upon the values of zeta, the stability can be determined as same as of the phugoid mode. Now if you can see the Dutch roll, it is the combination of yaw and roll together. For example, if the aircraft is yawing towards the left side direction, it also involves a couple that could roll. So simultaneously, if it corrects, again it yaws to the right, and again it induces the rolling motion in the right side direction. So that is how Dutch roll mode happens, and mathematically this equation is represented as beta double dot plus 2 zeta omega and beta dot plus omega n square beta, where beta is the side slip angle, damping ratio, natural frequency. Again, CG position defines the values of the damping factor. As it changes, the stability changes as follows. Now let us look at the roll mode. So this is the first order motion. As of now, which we have seen phugoid, short period and Dutch roll, these are all the second order motions. So roll mode is the first order motion which is not involving the oscillatory thing. It is the pure rolling about the longitudinal axis, and it is very fast and strongly damped. The mathematical model is given as P dot equal to LPP, where P is the roll rate. LP is the rolling damping derivative. If rolling damping derivative is less, roll motion decays quickly and it gives a stable condition. If it is equal to 0, it is neutrally stable. If it is greater than 0, it leads to the unstable situation. Now let us look into the spiral mode, slow motion, where the aircraft gradually enters into the spiral drive. We can look into the picture how it actually entering into the spiral drive and all. It is actually caused by the imbalance between the yaw stability, dihedral effect and roll damping. The mathematical model is again a first order motion which is given as phi dot A5. So the solution is the phi naught e power 80, phi is the bank angle. Again, depending upon the changes of coefficient matrix in phi dot A5, that determines the stability of the system. So this is how the CG position is connected to the dynamic modes and how mathematically the things changes and the stability determines. Thank you.
Once again, pretty good job in terms of sticking to the focus of the center of mass. So it's difficult to kind of correlate that to all these dynamic modes, because in reality, a lot of these linearizations may not work, but the simplest model, whatever is feasible, I think you've done a good job in presenting. The title of your subtopic was center of mass location. So just a simple question, is that the same as CG? Because CG is what I saw throughout your slides, not CM.
Yes, sir. We are considering gravity as constant.
So
Center of mass would be equal to center of gravity as long as we consider gravity as constant. But as we go higher in the altitude, as we go higher in the altitude, the gravity changes. So in that motion, if the gravity changes we consider, then center of mass is different from center of gravity.
Another thing, of course, Karthik has left for a talk, but as a team, you're supposed to cover for him as well. He mentioned in passing that static stability is a necessary condition for dynamic stability, but not a
Sufficient condition.
yeah. So, can you elaborate on that? Why is it a necessary condition? Is it not possible for an aircraft to be dynamically stable, even though it may not be statically stable?
I mean, static stability is the inherent property of the aircraft to return to the equilibrium position.
Okay.
So if it is not able to return to the equilibrium position, then we can't talk about stability.
What if you disturb it and it starts moving in the same direction, but then starts oscillating so that it will come back to the trim?
I'm keeping that.
So if you draw a response versus time, there's a disturbance in the response, right? So it is taken in a particular direction. Now for static stability, it has to come back in the opposite direction. Suppose it doesn't come back in the opposite direction, it increases in the same direction in which you disturbed it. But then after going for a while, then it starts oscillating and then it comes back to the original trim position. So that's not statically stable because the initial tendency is to continue along the direction of the disturbance, right? But then eventually it is coming back to the trim. So is really static stability a necessary condition for dynamic stability? I mean, you don't need to answer from aircraft perspective. It's simple stability question.
Yes. Like if it is, there is no initial tendency to come back, then dynamically we can't do it. Like with respect to time, how the stability was changing and how it is coming back to the equilibrium state, we can't show it, right? For example, if it is oscillating, like at this point, it is coming back to the initial state. Again, it is going. Again, it is coming back. Again, it is coming back. Like it is the necessary condition for the system to be statically stable for dynamically stable. Like it is coming back to the neutral point again and again.
Take the very simple example they show in introducing stability in all textbooks, the bowl with the ball, right? So I'm trying to push the ball. I'm saying that if the initial tendency of the ball is not to come down, but continues with that inertia to go a little further, but then eventually it will anyway come down. And so it is from the definition that we typically see, including in your slides, that is a classic example of a case where the system is not statically stable, but it is dynamically stable. I might be playing the devil's advocate, so I could have the if I'm wrong, you have to correct me. Okay. So before your next presentation on Wednesday, maybe you can just spend a slide talking about this. And it's not fair also because what that was mentioned by Karthik, so involve him in the preparation of that slide. Thank you. Anybody has any questions or right way? Okay, thank you. So you can continue. Same.
Extremely sorry for the delay. Good afternoon, sir. Good afternoon, everyone. So our topic for today's presentation is dynamic stability and how aerodynamic center affects dynamic stability. As we can see over here, aerodynamic center is just one actually invisible point, but it actually governs every oscillation in flight. As you can see over here, how the position of wing and the wing's aerodynamic center, it will basically tell where our neutral point will lie, taking into account the aerodynamic center of both tail and wing. And that neutral point will basically determine our static margin, right? Which is basically our measure of stability. And our static margin, which basically determines our pitch stiffness, that is our static stability. But when it comes to dynamic stability, this pitch stiffness is directly responsible for dynamic stability as well. And for longitudinal dynamic stability. And for lateral direction, we need to take into account wing geometry and aerodynamic center height as well. So this takes into account all 5 dynamic modes. First, I want to define what do you mean by dynamic stability. So static stability is the ability of an aircraft static stability is the ability of an aircraft that if it is deviated by wind gust or any kind of suppose elevator deflection, then what is its ability to get back to its original position, trim position. But dynamic stability determines how it will return to that position, whether it will converge to that position, whether it will diverge, how much time it will take to return to its original position. So in order to understand dynamic stability, we need more equations of motion. So this is the 6 degree of freedom equations of motion. Generally, for a normal performance measurement, we use 4 degree of freedom. And in order to quantify a moment, we actually add one more equation, the moment equation. But in order to understand dynamic stability completely, we need all 12 equations of motion. That is like 12 equations of motion in 12 variables. The 12 variables are basically the velocity in XYZ direction, U, V, W. Then we have the rate of change of velocity. Then the angles in all 3 directions, phi, theta, and psi. And also the pitch moment, pitch P, Q, R. This is the angular rate, change of angular rate in those 3 directions. So these 12 equations, they are non-linear in nature. So it's very, they're not analytically solvable. So what we do is, we change them from non-linear equations of motion to, in order to understand them at trim state. So we first basically specify a particular trim state. Basically, we just give U0 and basically specify other 2 velocities as 0 and all derivatives as 0, time derivatives. And then we give small perturbations across U. And then that is through which we then drop nonlinear terms, higher order terms. And that is the reason when we get this beautiful 4 equations, which are longitudinal set, and 4 lateral direction set, which are decoupled from each other. That is based on all our assumptions, that is like rigid aircraft, small perturbations, symmetric decoupling, and linear aerodynamics, small angles of attack as well. Now we can look into linearized longitudinal equations. As you can see over here, if we solve this particular equation in this format, we basically get these 2 equations. One is phugoid mode and another one is short period mode. As you can see over here, the one which is closer to the axis is the phugoid mode, and the one which is far away is the short period mode. So short period mode is high, is fast and has a higher frequency, whereas phugoid is lower frequency, it is lightly damped. If we plot them on the real imaginary axis. This is phugoid mode. Basically, it is when an aircraft, as height increases, its kinetic energy turns into potential energy. Then the kinetic energy again, basically the potential again becomes kinetic. It is that is how this aircraft goes in a phugoid mode. Angle of attack is approximately constant, and there's not much change in speed or altitude. It is not an angle of attack oscillation. The phugoid mode basically depends the frequency and this is the damping ratio. They both depend upon velocity and lift by diagonal. So it is not much dependent upon aerodynamic center. But if we put an aerodynamic center forward, then there is a large static margin, which basically means we need a larger tail or larger tail. That means increase in drag. So that can increase our damping ratio. So large static margin can increase our damping ratio, but by a small amount. It won't have much effect. This is like a typical forward mode time period and damping ratio. It's around time to half amplitude is around 4 minutes. As you can see over here, if you have a negative static margin, it will go under bifurcation, our route will become unstable. But if you increase our static margin, our forward mode will become stable. This is where our commercial aircrafts are at. And this is nearly neutral, 2% static margin, 8% is commercial aircrafts. This is a 15%, it is extremely stable for forward mode. As you can see over here, I've shown the same way in how the time response varies. This is for scenario A, like a very high static margin. It decays very fast, whereas for other, it will decay slowly. It's 400 seconds, 800 seconds. Constant amplitude, it will just go on. And if it is behind the imaginary axis in the right hand side, it will basically diverge. Now let us come to short period mode. So short period mode is much more important when it comes to instability in aircrafts, because for an aircraft to be given certification, it needs to ensure that it is in level 1 handling boundary condition, and that only comes when the damping ratio of short period mode is between 0.35 to 1.3. Compared to Foucault, short period mode is like higher frequency and less damping. As you can see over here, increase in static margin will basically take our short period mode becoming more stable. The left side makes it more stable, the right hand side will make it unstable. This is the generally where fighter aircrafts lie. This is basically they are unstable naturally, but when we add fly-by-wire systems and additional synthetic movement in the direction or in the pitching direction, that is when they become stable. This is, as you see over here, increase in static margin and basically increase our natural frequency. That is good for a short period mode. We want to increase the natural frequency. That will give us a stiff response. And this is the level 1 handling we need to maintain it in order for it to get certified as an air. So damping ratio versus static margin curve. Then we'll look into linear lateral directional state space equations. And basically these equations, we can basically bring them into this characteristic equation, which is basically a form of 3 eigenvalues. One is the spiral, one is the roll, and this is the Dutch roll. Roll is basically, as you can see over here, is a real root. Spiral is as well a real root, whereas Dutch roll is a complex pair. So spiral is very close to the axis. It's around 0.01. It is very slow real root. So it is really unstable. Whereas roll, it is a single fast real root. It is very stable. And Dutch roll is a complex conjugate pair. The stability depends upon the position of aerodynamic center and static margin. As you can see, I will come to this slide later. So this is roll subsidence. How roll damping? Roll damping is very simple. Roll is like the most simple dynamic modes. It is like first order decay. There's no oscillation, and it is very stable for a given for any given aircraft. Basically, it depends upon the wing sweep and wing panels. Basically, when an aircraft rolls, the lift over here increases and decreases. That will basically increase our roll rate, and roll damping will be basically LP, which depends upon the aircraft geometry. So, how AC? If you shift AC aft to the wing panels, basically this reduces the effective angle of attack during roll, which can make the roll slightly longer. So basically, lazier response, a slight shift in AC behind, but it's very stable. Spiral is the one we need to worry about. It is unstable. It can become unstable. See over here, an unstable pole can go over there. So we need to ensure, in order to maintain spiral stability, we need a high wind. Spiral stability is very much dependent upon the dihedral and yaw damping. So that is the reason we need a high wind, which gives us a positive dihedral, which basically ensures spiral stability. And low wind will basically make the spiral more unstable. It will shift our pole towards the real axis. Then it comes to Dutch roll, which is the most interesting phenomena. The reason why it is called Dutch roll is basically in the beginning the aircrafts were designed for generally sea level, but Netherlands, since it is like it is below sea level, the air density over there is much higher. That is the reason the first time the Dutch roll was observed. That is the reason it got the name Dutch roll. Right? And in Dutch roll, basically it is like the yaw and your roll is coupled. So an increase in roll will basically change the lift distribution. That will result in slight yawing. I will show it later. I have a very interesting video which shows Dutch roll. For any Dutch roll, we need to make sure that Dutch roll is very well damped so that it does not cause any kind of instability. For that, generally we use yaw dampers. All aircraft use yaw dampers for Dutch roll. And one thing that can help us in stabilizing Dutch roll is swept wings, basically because they push the AC behind the outer panels, and that will basically result in poor Dutch roll damping. So that is the reason yaw damper are very physically essential to handle Dutch roll instability. This is like all the what can I say, all the dynamic modes, 5 of them in a single pole zero map, as you can see over here. When we go closer to it, we have spiral and phugoid, and then Dutch roll, short period, and roll. And this is like what is the primary influence of aerodynamic center on each of them. Is the time period, omega, natural frequency, and as you can see over here, primary influence is on roll is minimal. Basic most influence of AC is on direct influences on short period, and it has a moderate influence of Dutch roll and spiral. Next, this is a very common phenomenon that we discussed in previous presentations as well, like how as we go across the transonic region, our aerodynamic center shifts completely. It goes behind, and because of that, we need a very heavy tail in order to manage it. That can reduce our static margin as well, as our aerodynamic center is shifting behind. Our neutral point will also shift behind. So the thing we need to do, this can actually cause destabilizing in phugoid mode. As you can see over here, it can basically, as static margin decreases, our omega n will decrease as well, which is basically our handling of short period will reduce. And as static margin increases, our damping ratio for phugoid mode also drops, which basically gives us neutral oscillation. So phugoid will be not damped as well as it used to be early. So when we go through this particular zone, we need to take care of these two modes. It won't have much effect on roll and spiral or Dutch roll. This is basically a time response for the how across static margin. So at a very high static margin, we can see over here, phugoid will decay in 250 seconds. It's very acceptable. We will have level 1 handling qualities for a short period, high frequency, very high damping as well. It will reduce very fast. Roll subsidence is fast always, like you can see over here. Even when we change static margin, it is always very stable. Spiral will be stable as well. And Dutch roll, basically we need yaw dampers. Without yaw dampers, we can't do anything about Dutch roll. As you can see over here, if we reduce our static margin, our decay basically increases. Our time decay is 500 seconds now for phugoid. Then it will be barely damped. Then it will become a nuisance if we have a very small static margin. If a negative static margin, basically it will bifurcate and become unstable. Same goes for short period mode as well. A moderate static margin, it will be good. After that, it will basically be very sluggish. If it's a very negative static margin, it will diverge, it will become unstable. So this is basically the regime in which fighter aircrafts fly. Still, so they need fly-by-wire. That is the reason, in order to avoid short period instability. And we can see over here, spiral as well will break down. It will also become unstable and will have unstable Dutch roll as well with negative static margin. Now I will come to my previous slide. This is how a pilot feels when short period step response. As you can see over here, with a high static margin, it will be basically a stiff response. Like it will may feel harsh, but with a moderate static margin, moderate aerodynamic center, it will be like a balanced response. So even though this is stiff, but it will damp very faster. but if we reduce the static margin, it will not damp. It can cause problems. This is the position of the one and position of the second root, and this is for 2% static margin, which is aft aerodynamic center. As you can see over here, it will be sluggish and it can be very problematic when it comes to turbulence. Unstable, it will be basically an open loop. It will be uncontrollable, diverge, and it will diverge in seconds. It can cause massive accidents. So this is to summarize what we are looking to now. So the position of the aerodynamic center, one single point, it will determine static margin, which along with pitch stiffness will determine the stability of short period and Foucault. And if we take into account the wing geometry, that will determine our three lateral directional modes, roll, spiral, and touch roll. And these are the key equations. And this is the same physics which is applied to all kind of aircrafts. Now I will basically this is not that interesting. It is just a paper where they tried to find this particular dynamic modes for short period moments and moment coefficients, and they were able to get a much better result. This is their prediction. This is the wind tunnel, and this is CFD. So it diverges at high angles of attack, but it was very close. So it is basically, it's called a vortex particle method. So it can it can give accurate result up to ±5% against the experiment. So the usefulness of this is basically solve the cost problems, because we don't need to do expensive wind tunnel tests. Basically, we can use this method to calculate the coefficients, moment coefficients. Now this is the video I'll play. Click it. Okay, is it? Okay, I'll show this video at the end. Now I'll invite my friend Deep to continue his presentation.
Good afternoon. Okay. So now I will talk about the various case studies. So first is the commercial aircraft. So in commercial aircraft, the static margin is kept at around, for in the case of A320 Neo, it is 7 to 10%. For 737, it's 8 to 12%, and for A380, it's 9 to 14% with a trim tank. Okay, so now when the aircraft takes off at first, the static margin remains higher as the aircraft is loaded with fuel. It is at full fuel capacity. Now, as the aircraft cruises, its fuel decreases, it burns up, and its static margin then decreases to about 12%, as you can see in the right plot. And during landing, the static margin goes closer to the lower limit. For example, in case of A380, it's about 9%. So this is how the static margin varies with flight hours. This graph is given for about a 7-hour flight time. So initially, when the static margin is higher, the controls feel stiff and responsive because of the short period dynamic modes. But as the flight progresses, the control starts relaxing. Now coming to fighter aircraft. So in case of fighter aircraft, we have relaxed stability and negative static margin. So the bare structure itself is naturally unstable and it falls on the unstable regime. However, the flight control system, which is basically the fly-by-wire system, it adds synthetic pitch moment, and it brings it in the stable regime, as you can see. And why do we need like lower stability static margin? It's because as we decrease the static margin and go towards the negative static margin regime, our instantaneous turn rate, as you can see on the rightmost plot, it increases. So the aircraft becomes more agile, which is required for fighter aircrafts. Now there are some unconventional designs also. For example, in the first case, the twin otter, which is a stall aircraft. So in case of stall aircraft, we have higher static margin, but our aerodynamic center is above the CG, due to which we have a high CL beta, leading to higher yaw agility and lower yaw stability. Then we have UAV designs also. So the last UAV design, which is the X47B, which is a tailless design. In this case, the neutral point is very near to the CG and static margin is pretty low. So in this case, again, fly-by-wire type system is required to correct it. Now let me talk about the difference between the crewed and the autonomous design philosophy. So in case of crewed aircraft, we need the human pilot feel. So as a result, we need positive figure damping, and so the static margin should be locked within 3 to 20%, even if it includes FBW, fly-by-wire. So that may also bring it so that human pilot feel is taken into account. While for UAV, you don't need the human feel limits. So as a result, if FBW is fast enough, we can have negative static margin also. So we can have a higher range of aerodynamic placement as compared to those human flights or human airplanes. So now coming to extreme AC management. In the case of Concorde, the AC is managed, sorry, the CG is managed by pumping fuel. Like when we are accelerating towards higher max speeds, fuel is pumped backward to take into account the Mach tuck, while when during deacceleration the fuel is pumped forward. This has been discussed already in the previous presentations again. So what if the fuel transfer now fails? If fuel transfer fails, then in that case it becomes unstable due to Mach tuck within 3 seconds. And even if you try for manual trim compensation, it will require 5 degrees nose down L1. So as a result, there will be a 30% drag increase, and so we can't have supersonic cruise in case of Concorde in this case. So now coming to wing geometry effects on effective AC. So we have different kinds of wing configuration, wing geometries which is possible. In case of the straight wing, as you can see, the AC position doesn't change, it remains predictable as the angle of attack increases. For moderately swept wing, like 30 degrees swept wing, which I have given here as example, mostly the aerodynamic center remains at 25% mean aerodynamic chord, but due to the tip stall zone at high angle of attacks, what happens is that AC shifts F suddenly as angle of attack increases. While for high aspect ratio wing, in case of a sailplane, the aeroelastic bending dominates. So as a result, what happens? The AC position goes forward at higher angle of attacks by a slight amount. While for 60-degree delta wing, what happens? Leading edge vortex dominates, vortex breakdown happens. As a result, the aerodynamic chord, it migrates F very sharply. As you can see in the plot also, the AC migrates F very sharply. So as a result, we have a pitch up tendency for the aircraft, and this kind of delta wing design is again used in a lot of fighter aircrafts because of agility. Next comes the aero elasticity. So what happens is that, so what happens is that the effective AC, as I've already said, because of aero elasticity, it moves forward. However, we design the wings in such a way that it does not go behind the elastic axis. So it must always remain forward of elastic axis to avoid divergence. And at higher velocities, flutter dynamic coupling happens. So both the bending frequency and this dynamic frequency, they converge, and this leads to flutter, which is a non-linear dynamic problem, and it can cause difficulties for the aircraft. Then comes the comparative radar chart. So again, different aircraft are basically made for different missions, and accordingly the static margin and the dynamic modes are taken into account. So these are the different aircraft and what they specialize in. So for example, in case of the B2 bomber and the F-16, we see that they are not optimized for any of these parameters, like for example the natural static margin or Fugger damping or any of them, while aircraft like the A320, the commercial aircrafts, B747, then even the Global Hawk, which is the stall aircraft, they optimize for natural static margin and natural Fugger damping and everything else. So now coming to the limitations and interpretations of the theory. So this dynamic theory fails, like it has limitations for, as it takes into account linear aerodynamic limits, so it fails above alpha equal to 15 degrees. Then our assumption is all based on small perturbations, but during stall or high angle of attack that may not be possible. Then you have rigid aircraft limits, so it ignores the aeroelasticity part which I discussed. Then Mach number is ignored in the first pass analysis, and uniform downwash is assumed at the tail, which is not the case always in real world. So these are the two cases. In the first case, there may be ice deposits, like which are not taken into account. While in case of the delta wing, as I had already said, there is high AOA vortex background. There are complex interactions which are not taken into account in the simple theory. Then a bit about the fly-by-wire pitch augmentation. So this is the entire flowchart of how the fly-by-wire pitch augmentation is taken place, like how it gives the artificial pitch moment which stabilizes the aircraft. So it takes into input your pitch rate, the angle of attack, as well as NZ. Then it's fed into the FCS computer, which gives inputs every 40 times every second, and accordingly this goes to the elevator command, and accordingly it gives the artificial pitch. Now, as you can see in this plot, there is this circle, like red circle. So this is the stability augmentation bandwidth, which is limited by structural mode frequency. So within this only it can give the artificial pitch moment and stabilize the aircraft. Beyond that, it won't be possible even for the stability augmentation system also. So now one of the case studies is the MCAS warning. So in MCAS warning, what happened? So due to MCAS whenever that angle of attack sensor, which is one of the sensors out here, it turned out to be faulty. So it used to pitch down the aircraft at a dangerous level, which led to disasters. Like two crashes happened because of this. So now coming to the certification interface. So this is the Cooper Harper rating scale. So there are 3 levels. It's first divided. The scale is divided into 1 to 10, and it has then divided into 3 levels. So level 1 is excellent negligible deficiencies, which is where our aircraft handling should be by design. Level 2 is adequate for non-normal conditions, while level 3 is controllable while unacceptable, while the last level 10 is uncontrollable, and no aircraft should be designed in such a way. And this scale also includes like fly-by-wire systems also, like how fly-by-wire brings it into like level 1 if the aircraft structure naturally is, for example, say in level 3 due to negative stability margin and so on. So this is the short period boundary chart. So within the green region, naturally we have A320, B737, 800 and so on. One important case study is of F-16. So F-16 is naturally unstable, so it lies on the outer edge of level 3, but by using fly-by-wire systems we bring it to the green zone. So this plot is basically between damping ratio and natural frequency. So in the green zone, both the damping ratio and the natural frequency are quite low. They are not on the higher side. Now coming to the economic side of the things. So if we have our aerodynamic center to be very ahead, like it's very ahead, in that case what will happen, we will need a larger tail to compensate and bring the neutral point behind. So as a result, we may have for example, suppose we have 1% excess static margin. So this will lead to a higher tail area by 0.3%. So this will increase the structural weight by this amount, and as a result, the fuel penalty per flight will be about 0.05%. So if we take a calculation, suppose we have 200 A320s, in that case, we will have to pay, like the airline has to pay 20 million per year fleet excess cost just because of 1% excess static margin. While on the other hand, this A320 means Airbus aircraft have trim tanks. So by fuel pumping, trim tank shifts the CG eft. Now, if the CG is eft, that tail size which we require additionally is eliminated, and trim drag can be reduced by 1.5%. So for single aircraft itself, we can have a savings of 2.75 million per year. While on the other case, if we have a very wrong AC management, which is the catastrophic MCAS system which you discussed. So in the previous presentation, I had also discussed that the LEAP engine was moved the aerodynamic center forward at high angle of attack. So as a result, they implemented an MCAS software system. So MCAS then misapplied nose down correction without authority limits for high angle of attack. Like if the angle of attack sensor was wrong, then in that case what happened was it did a nose down unnecessarily, and this led to disasters, as we know. Then in case of Concorde also, there is a 15% transonic fuel penalty. So this is the relative economic impact of the various AC management decisions. So active trim tank, for example, saves 10 million, while MCAS type failure resulted in a loss of 20 billion, plus 300 people also lost their lives because of this. So this is the this is here I conclude the presentation. So this is the physics. These are the equations which we summarize, which has been used here, and these are the various cases, like what happens if a forward AC, aft AC, transonic migration, Mech tuck, and the various researches which is happening, as he has mentioned. So thank you.
Wanted to show that video?
Yeah. Okay. So that video. So we are now showing the video for the Dutch roll, which he had said we will show in the last.
As we can see over here. Good. That is how Dutch roll is. So both roll and yaw are coupled. Goes across like this. And this is for a Boeing plane. They are testing it for Dutch roll. And they require now they are using yaw dampers to basically damp the motion and then land the plane safely. Yeah. So with this, I conclude this presentation. Thank you. No, it is testing. Yeah, testing. Yeah, they were testing yaw dampers, how they are working, how yaw dampers are working too. Yeah.
Anybody else?
In Dutch roll, you told that they have a complex conjugate pair.
Yeah.
So why they have a complex conjugate pair, and what physically signifies that conjugate? And in one of the slides, you told that in transport aircraft, when fuel is burned out, their CG location is shifted. So why they have not designed their fuel tank such a way that they are near the CG and it's not change so much, so that your static margin will not change?
Okay, one by one. I'll first come over to Dutch roll. So as you can see over here, the equation for Dutch roll is this one. The third characteristic equation. As you can see over here, there's a second order equation. So it has two roots. And since we know, like basically, if you solve a quadratic equation, if the determinant is less than 0, then it will give us complex roots. That is the reason behind complex roots. And yeah, that is the reason why Dutch roll has oscillations.
Complex root physically signifies?
Complex.
Why you don't have only one value, but you have a pair?
The pair, the reason we have a pair, basically it signifies oscillation. Basically, like if you look this is I omega, and this is S, right? Sigma, sorry. Sorry. So this particular value is theta omega n minus theta omega n. This is omega n square, which is the radius of the circle. And so the complex pair, as you can see over here, it is minus theta omega n in the on the x-axis, on the sigma axis, and on the y-axis, it is basically what is it? I'm not sure about it, but so I forgot.
You have I omega.
Huh?
You have I omega
Hmm?
in a vertical. You have sigma in a horizontal.
Yeah.
So my question is, if I get a conjugate pair, so in a physical sense,
So what does it signify in the physical sense? That
Yeah,
is what you're
physical
asking. Okay, fine. With physical, in the physical sense, it basically signifies oscillatory motion. That is it.
but which oscillate? You have already shown in video.
Yeah, exactly. It's oscillatory, right? Your single root, it will
In pivot you have
see.
also
This is
oscillation.
roll. We have
But you have a one value. But here we have a pair.
see in roll we have one value, one eigenvalue. So it is basically the equation. If you plot it against time, it will be a single decay, no oscillation. Whereas in case of Dutch roll, it basically doesn't occur, but it is very similar to this one. It's basically oscillatory.
As far as I learned from your PPT, that I think conjugate pair is due to the coupling between your yaw and roll. That's why we get a conjugate pair. If there is no coupling, then you will get just a one value of
I mean, for longitudinal modes also we have two conjugate pairs.
yeah. So,
but there's
so
no coupling.
what that also I don't know
Yeah,
why
exactly.
we get a conjugate. If it's just a Fugard mode, so it also should be a physically dictate something.
Yeah, I mean, see, like if we
In
get
mathematical
conjugate,
sense, we know that which parameter dominate which part. But in a physical sense, if we get some simulation and we get some value, but I don't know how it physically looks like, and I want to detect that motion. So, and also the second part, which I
what was your question? Can you please
the
repeat?
second question is in one of the slide for a transport aircraft, as the fuel burn out, their CG is shifted. So why
Yeah.
they have not put fuel tank such near the CG, so it will not happen. So what's
So generally, the fuel tanks on an aircraft is located at this wing, right? If
Yeah.
you look at an aircraft from this location, this is where most of the fuel tanks are, right? Since once wing design is done, we can't shift the fuel tank, right? And but there are
But
systems like
how much it will change that? Yeah, shift is minimum or it's a larger or
huh? I mean, this fuel will be used first, so aerodynamic center will definitely change, right? That will change your static margin. Yeah. What was it? Yeah, it is a physical limitation. Yeah, exactly. Yeah.
it's like yeah, but if I make a aircraft such a way that with fuel and without fuel, my CG is just if with fuel my CG is near to the wing, and after fuel after whatever fuel burn, my CG is just shifted, let's say uh, just behind that point, so it doesn't change so much that static margin, and the plane your aircraft is still stable, so you don't have to worry about yeah so that point I want to
Yeah. Yeah.
Explicitly about this one. They are not allowed to cross that. So there will be situation which is not provided, but then there are bounds.
I think Srichar is doing a very good job answering my questions. You should also join us here next time. We need your help. Okay. Anything else?
Thank you. Thank you. Once again, really comprehensive presentation covering a lot of different aspects of the problem. That's pretty good. But still, some of the things that I pointed out last time, like for example, the static margin being shown, apart from the, see, typically when you're looking at static margin, it's the distance between the that you have over there that can be visualized only in the side view or the top view. But there are some frontal views also where the static margin is shown, which is what I had pointed out last time. So I thought you'd avoid that this time, but it was still there. So I'd like you to take a little more care next time onwards. Because same kind of mistake I don't want you to repeat. You can be innovative in some of the mistakes also. So then coming to, also thanks for that etymology of the Dutch roll. I was not aware of that. Of course, Netherlands means it's under the sea and therefore the density is large. So that explanation is interesting because a lot of people explain that through ice skating. So ice skaters, if you have observed, they typically operate in pairs. And some of the maneuvers that they do, especially the Dutch teams, and now of course it's done by internationally by all the teams, is very similar to the mix of the roll and the yaw. Okay, so that's one explanation which is typically given. Okay. Then I had a couple of questions from Surabhi. One of these slides you had shown, I believe, low static margin is associated with high damping. So what is the explanation for that?
In which slides? I think I have shown that low static margin is high static margin associated with high. Low static margin is basically high static margin will have higher frequency. Low static margin lower.
Yeah, so again, it boils down to what Yesh was asking also in terms of the real and the imaginary parts, what significant roles they play. How does the static margin, because your main question is about the aerodynamic center position, how it affects. So, which in turn translates into static margin directly, right? So, from that point of view, is damping really affected, and if it is affected, in what way? By static margin being small.
Static margin is very small. Yeah, this is a very good example. You can see all the files I have shown you. For convert it is very damp. For short period access, it is sluggish. For roll, it doesn't matter because it is a very stable damp. File can be mildly unstable, and that shows its angular distribution. I think that is what the small static margin is.
No, I don't know if it's this slide or some other slide she mentioned. That's okay. Another thing she mentioned is the sweep effect in initial slide was a contradiction. When you go to where you explain the sweep angles and how they affect the static margin and therefore the dynamics.
Is I'm not sure it's within the initial slide. Actually, this is the only slide where sleep is sleep will delta. Sleep is shown over here. And actually, I got like as this too. Actually, swept is basically push the AC app on the outside, and that's basically is poor industrial app.
Sir,
Yeah.
sir, as you about real part is dictating the damping. So if they have a larger negative real value, so they have a consequently higher damping, and imaginary part dictates how my response is there. So it's just a like bubble. So if we have a higher negative value, so it have a higher omega. But if I have a real negative value, so it will drift out faster way. And if it's near to that even line, so it ever lower temperature.
So those pairs that you are talking about,
Yeah.
so
the real
complex
part
conjugate,
indicating
yeah.
the damping part.
correct. The pair that you are talking about, it essentially is about the frequency.
Frequency that
So,
the vertical
so,
part is
so if you have only a real solution, your omega n is 0.
Yes.
So that's what he was trying to explain, that essentially it's not oscillatory, it's just either divergent or convergent. Okay, anybody else? Otherwise, we'll conclude. Thank you. Thank you.
Shall we start, sir? So, good afternoon, everyone. Team Blackbird here with our 7th presentation. Today, we are short of one member. Alvin is not with us today, so he has some commitments. So, our topic for the afternoon is effect of static margin on dynamic stability of an aircraft. So these are the subtopics we are about to go through today, and I'm Edil. I'm gonna take up the introduction for now. So we know that stability of an aircraft is an important aspect considering the safety. Previous week we might have dealt with the static stability of an aircraft, which says about the initial tendency of an aircraft to reach its equilibrium position following a disturbance. But that in the initial tendency is alone not enough to judge on the overall stability of an aircraft. So in order to complete the comment on the overall tendency of an aircraft to become stable, we introduce dynamic stability, which traces the how the motion of an aircraft evolved with respect to time following a disturbance. So this dynamic stability of an aircraft focuses mainly on the rate, magnitude, and the nature of oscillation that the aircraft undergoes whenever a disturbance is occurring. So this is the basic definition of dynamic stability, which I just said now. Tendency of an aircraft to return to its equilibrium state with time after a disturbance, considering the time history of motion. So based on the path traced by an aircraft in order to reach the equilibrium position, we can classify the dynamic stability into 3: dynamically stable, neutrally dynamically stable, and dynamically unstable. So a dynamically stable aircraft following a disturbance tend to have a gradual decrease in oscillation, and over time, and over a period of time it reaches the equilibrium position. So this is the general flight path taken by a dynamically stable aircraft, that is a damped oscillation. So for a neutrally dynamically stable aircraft, the aircraft tends to be in a continuous oscillation irrespective of time, just like depicted in the picture as well as on the graph. So that's the flight path for a neutrally dynamically stable aircraft which has no damping, that is an undamped oscillation is happening. So for a dynamically unstable aircraft, there is an amplified oscillation causing a very off distance from the equilibrium position, which is also depicted in that graph, with an increasing amplification of the oscillation. So stability margin, we might have come across this basic term an umpteenth time in our previous topics. So the stability margin is the distance between the center of gravity and the neutral point of an aircraft, expressed in terms of mean aerodynamic chord. So this stability margin plays a crucial role in determining the dynamic response of an aircraft, influencing the restoring moments, damping characteristics, and the overall behavior of the aircraft following a disturbance. So further how and all will be explained by my teammates.
Hi, I'm Vishal and I will be presenting the effect of stability margin on fugite motion. Basically, that's the longitudinal characteristic equation. It's a fourth order equation, and solving for it, we can get two modes: short period and the fugite mode. And the figure on the below shows the fugite oscillation. It's basically like a roller coaster ride, and it's oscillate with respect to altitude and velocity. It's basically exchange between potential energy and kinetic energy. The figure movement's characteristic is such that the angle of attack is remain constant. So the rate will remain 0, and the fourth order equation now reduces to a second order equation. Solving for its eigenvalue, we get in the form A plus or minus IB. And from that, comparing with the typical second order equation's eigenvalue, we can get the damping ratio as minus A by square root of A square plus B square. Now, analogy with the spring mass system. This longitudinal dynamic stability can be analogous to a spring mass system with a damping value, and we can think of a static margin as a stiffness of this spring mass system. So when aircraft is disturbed by a gust or something, the the static margin, which is basically a negative of the dou cm by dou cm by dou cl, it will tend to bring the aircraft to its original position. So it can be thought of as a stiffness. And here cm alpha is equal to minus cl alpha into cm. Yeah. Cm alpha is equal to, dou cm by dou alpha. By chain rule, we can write this as dou cm by dou cl into dou cl by dou alpha. This one, as explained earlier, it's just negative of static margin, and this is cm alpha. So we get the equation. So when the static margin is large, it just means that cm alpha is large too. Now, this is a graph from the book Aircraft Stability and Control by Perkins. This will explain the effect of the static margin on the phugoid mode. Here, dcm by d alpha is nothing but a negative of static margin. So minus 0.01 means static margin is 0.01. And as we go along this direction, the static margin increases. So that means the CG is moving forward. These are the parameters for this data. And it can be seen from the graph that on the extreme left case, the static margin is very low. In this case, static margin low means cm alpha is lower, which means its aircraft's ability to go to the, maintain that angle of attack is low. So there is an instability over here. Basically, this y-axis is A and x-axis is B. A is a damping constant. When A is less than 0, basically the phugoid mode is stable, and when A is positive, the phugoid mode is unstable. So this is the stable region, and here the phugoid are unstable. So, and in the case of the leftmost point, when the CG is way too forward, when static margin is very large. Similarly here, like I explained, the static margin can be considered like a stiffness of an aircraft. So here dou cm by cm alpha is very large, so it's sort of like a overcorrects. Even for a small change in velocity or angle of attack, it basically overcorrects, and there is an instability related there. So this is the like a sweet spot. Here the aircraft, the phugoid mode is highly stable along this range of static margin. So it can be seen that the time period of the phugoid mode is directly proportional to 1 by the value of p. So as we go from right to left, as the CG moves backwards, the time period increases. Yeah, that's it. Thank you.
So I'll be explaining the effect of static margin on short period oscillations. So I'd like to start off by deriving this equation in the first line. So we take the linearized pitching moment equation. Here Iy is the moment of inertia of the aircraft about the y-axis, and q is the pitch rate. M alpha is the pitch stiffness derivative. This way, construct dq is the pitch rate. Kinematically, we can see that this has already been derived by the previous. So how we apply this is basically, let's say this is the horizontal and this is the flight trajectory, and this is the x-axis. this as the flight path angle. And this is the angle of that. And this entire angle is the pitch angle. And the change in the pitch angle is relative. We are assuming that the flight path angle is constant in this case, so all the pitch range is determined only by the change in the angle. So that's why we do this. Substituting this in this kinematic relation in this equation, we get a second order only. Then comparing that with the standard second order system, and we can obtain the natural frequency as angle calculation. So now, if we see about any aspects, we will. So here Q is the dynamic pressure, S is the surface area of the pit, C dash is the aerodynamic torque, and this, like Vishal had already explained, if we can write this as minus the so if we substitute in that equation, we can find out that since the pitch difference deriving directly proportional to static, the natural frequency directly proportional to square root. And similarly for damping ratio, we can find that since the pitch stiffness derivative is directly proportional to static energy, damping ratio is inversely proportional to square root. Now we may ask if the pitch damping ratio, that is MC, wouldn't that actually depend on the static what it actually does. You can notice that this formula is given by so this doesn't depend on the static method. So M is the M alpha is the only term that's actually used. So as a summary, I would just like to mention that high static method, like we say, can make the pitch to be very stiff and the natural frequency would be very high and the damping ratio would be comparatively lower. This would cause the flight characteristic to be very pitchy and prone to overshoot. Whereas low static method, like static CP, cause pitch to be soft or pitch stiffness to be very soft, and this causes sluggish response and slower return to the and correspondingly the natural frequency would be low and the damping ratio would be high. And then neutral static method, like when the CGs are we can notice that as any like it should be a neutrally dynamically stable system where it would have no return errors.
Positive lateral stability and it has to be direct to stability. So let's say is stating where we have instead we have more lift capacity. So as a result, rolling out will take place, and as a rolling will induce that energy. So this will get from as a new frequency, the velocity will reduce and the other side will come. And the same state will between the this will cause the control in the actor. There you can see the video of how they are attacked. Let's say how the depth is affected by the static that's happening again. First, let me derive the expression for the depth space. Right? Let's say this is the grade of the vertical grade of the pitch, and this is the response. So the aerodynamic center of the tail, let's say, force is here, and the restoring force that we is acting up here, and the CP. So the tail will be the difference between the aerodynamic center, which is given here, and the movement is as we know, it's a force into the aircraft. So from this we can get the dCm by d beta value. First, lateral stability should be always greater than 0. And we finally got the dCm by d beta value, where the eta v is take effective, which is the ratio square of velocity and take velocity. And we reach the train volume, vertical tail volume ratio, gravity ratio. So this ratio of that B is the wingspan and X is the area of the wing, and L is for the vertical tail and that is a vertical tail. So as you can see, since the static curve is not directly related to the lateral stability, but we can correlate the vertical tail down and the lateral stability. So as you can see, if static margin is a position of neutral point than CG. So if static margin decreases, then CG will go to the aft location of the wings. As it goes to the aft location, the tail distance will reduce. So we can conclusively say the stability of the latest stability will decrease as consequence. As stability will, the natural frequency has stability of the tail. By the relation, we can say that this is the relation which gives the relation between natural frequency and the lateral stability. So if as then between the CT goes to the application, the lateral the stability reduces and consequently the natural frequency reduces. So as a result, the damping ratio also increases, and the natural becomes more unstable, relatively unstable than the normal CT. Let's see, next we have spiral instability. Similar to the dashboard, but here we have positive dashboard stability and less amount of lateral stability. As a result, the atom will make a spiral around, but due to the specific roll movement and then the nose down movement is constantly reduced the decreasing the altitude of the aircraft. So it is still extra and the answer will go as we mentioned here, and as the altitude of the radiation also will decrease. The stability of spiral is given by this relation, while E is constant. So for the stability, the E should be greater than 0. As CG goes to the application, the NP will reduce. If the NP is reduced, if the volt level comparatively less to compared to the display, we can say that spiral the stability will reduce as location goes, and the CG goes to the application. So we can say the spiral becomes more unstable when the speed is to the forward. Thank you.
I think you did a really good job because most people, when they talk about static margin, they would only talk about the longitudinal dynamics. But I think you brought out Balakumar in particular the lateral and directional dynamics as well, which is a really excellent job in terms of the reduction in the distance of the vertical tail from the CG, and therefore the overall effectiveness of the vertical tail towards stability. Also, another thing which was good was I think even though you might have prepared separately, the slide design was kind of uniform, so it made it like a team effort rather than an individual presentation. So appreciate that as well. Okay. One request I would have, not only from you but the other teams as well, especially for those with accessibility issues from a visual perspective, if you can avoid white backgrounds and use darker backgrounds, because we typically tend to move towards dark mode these days, especially because we are having presentations continuously for 2 hours. So if you can have a dark mode, that would really help. I mean, it's also traditional. We always talk of a blackboard, not a whiteboard, which of course is hidden behind this slide, the interactive whiteboard. So that's one thing. Coming to the technical aspect, I really liked your derivations on the board. But MQ, you seem to have written from memory, though it's a simple derivation. Can you just explain how you get that LT squared there? It is correct, but I just want to know if you have given a thought to how it comes. Yeah. Why is MQ proportional to LT squared? Can you just explain that? Qualitatively also, if you don't remember the actual derivation. No, it's not all that difficult. If you can just probably sketch the wing and the tail, because this is essentially horizontal tails effect, right? So you sketch wing, and then little behind you sketch the cross section of a horizontal tail. Yeah. Right. Now you are about the CG, you have that Q, right? About the CG, you have a rotation rate, which is Q, your pitch rate, right? Nose up pitch rate. Yeah, you can mark that as LT. That's correct. Yeah. So those are the aerodynamic centers. You mark the, that's also aerodynamic center, or the CG. Okay, LT is from the CG. Okay, then about the CG, there is a pitch, right? So you draw your Q. So that's a pitch rate. Yeah, good. So that is not a pitch angle, but a pitch rate, right? So what will that do at the aerodynamic center of the horizontal tail? Yeah. Not the force, but it's a angular velocity, right? So that angular velocity, what will it cause at the aerodynamic center of the horizontal tail? If you have this, let's say this is the CG. CG is so now this is the horizontal tail. Now we are having a pitch rate. Positive is nose up. So we are having that pitch rate. So what? That is the angular velocity. But what is it? What happens to the aerodynamic center here because of that pitch rate? It phases up. Yeah, it goes down. It goes down, but it's a translational velocity. See, here it's an angular velocity, but because of that distance, non-zero distance, it is having a vertically downward velocity. So typically, of course, there's a downward and other things, but there is a velocity with respect to the wing, and then there is a velocity with respect to the tail. Now that velocity with respect to the tail, because of the pitch rate, will have a W component as well. So, exactly. So that angle of attack, what is it in terms of? Suppose there is a W. So it's just W for small angles, it's just W divided by V. So W divided by V is the change in angle of attack at the horizontal tail. Now that change in angle of attack is what we've written there, CL alpha T times. So the change in angle of attack is brought out as W divided by V. Right? And that W is nothing but because again it's linear, it's Q times LT. So Q times LT is W divided by V. So one time you are getting LT because of the pitch rate to get to the change in angle of attack as you agreed before. And then again you are getting the moment. Because you want to get the moment, again you are multiplying LT. So that's why you are getting that. It's good, it's numbered it correctly, but it's a very simple logic. Yeah, good job. Anybody else? Any questions for that? Okay, thank you.
Yeah, so good afternoon. We are Team Turbulence, and our topic is decoding the dynamic stability through damping. So, in a previous presentation, we already learned about how static stability affects the aircraft performance. So now we are going through the static stability is just indicate like its initial tendency towards to stabilize the aircraft, but it doesn't tell about in how much time it will go to the stable point, or if the system is really going towards the stability or becoming unstable. So our topic is explain the dynamic stability but through the phenomena called damping. So this is the one of the famous incident happened in 15 November 1967. The incident is like that. NASA has developed one aircraft called X-15. So how they are flying X-15, that they are using a liquid propulsion engine. So they are using B-52 to mount X-15 on that B-52, and they are flying at around 45,000 feet. So at that height, they drop the X-15, and from that they ignite the liquid propulsion, and then the X-15 will move. The first thing is X-15 is already a statically stable aircraft. So it doesn't like that. It's not a static stable aircraft. So their CM alpha is already negative and it's highly stable. But when the aircraft, the pilot called the Michael J. Adams, when he flew from 55,000 to 2,66,000 feet. After flying that flight, they are trying to mimic some wing rocking phenomena. After doing wing rocking phenomena, because they have planned certain type of test they have to perform while testing this aircraft. So at the time they have done a wing rocking. Secondary, in a previous X-15 flights, they have encountered so much technical failurity, but any failurity doesn't lead towards the fatality. So in this at the time when Michael also is flying, they have some issue in their control system designed by Honeywell. So what happened that while testing that wing rocking, the yaw, they have come up with some yaw perturbation, but in a flight controller they only have a screen called a pitch rate. The aircraft is only showing that when the X-15 is pitching up, so it's showing that it's a 15 degree moving towards nose up movement. But at that time the yaw have also perturbed from its position, but due to the flight controller doesn't have that yaw capturing moment, that's why Adams doesn't know that the aircraft is already yaw, because it's happened the yaw, and they have some due to that delta wing configuration, they induce the roll effect, and by coupling that roll and yaw such a way that the pitch also get influence, due to which the while due to this phenomena the aircraft is re-entered, and at that time it experienced the 15G load, which is the structure it's can't able to sustain that much of 15G load, due to which the aircraft is failed. And after that they have diagnosed this phenomena, why this happened. So as we know that at that height, 2,63,000 feet, the air density is so much low that the aerodynamic dampening is not there. Also the yaw, roll and pitch, three of this effect is influenced simultaneously such that it doesn't have atmosphere to slow down this effect, due to which they can't able to control this stall, and also they have the issue in their Honeywell flight control also, which lead to this failure. And also the NASA has already documented this failure, so you can read that research paper. Now others will talk about.
Now we'll talk about the three cases. First is pitch damping. As you can see, when aircraft pitches its nose up, the tail sweeps downwards, due to which it induces an upward local relative wind. And because of this, the tail's local angle of attack increases, which generates extra nose down movement. This is opposing the pitch movement that was nose up. So this is pitch damping. Second is roll damping. When aircraft rolls, the descending wing sees a higher local angle of attack, and the ascending wing sees a lower local angle of attack, which due to which difference in lift created, which results in the opposite movement. Also, the third case is downwash lag. Here you can see the distance between the main wing and the tail is LT, and when the main wing pitches, the change in its trailing downwash takes time dt, which is equal to speed distance upon speed. So LT upon V, this is the time the changes take to reach the tail. So this physical lag creates a hysteresis loop, extracting energy from the motion. Now, first we'll consider the sign convention. We are using strictly right hand rule. So I cross J is equal to K, that sign convention, and we generally take four mathematical simplification. First is rigid body simplification, but it fails at high aeroelastic deformation and high dynamic pressure flutter. Second simplification, we take constant mass like dm by dt is equal to 0, but this also fails like in rocket case when fuel burns at a very faster rate. Third simplification, linear aerodynamics, but this also fails at flow separation. And fourth simplification is small perturbation, but this also fails during inertial coupling, like what Yash told in previous slide. Now Yash will continue again.
Yeah, so from as per assumption, we are trying to go with the mathematical derivation that we know from the pitch moment formula that I theta double dot is equal to the moment created by the aerodynamic force and moment created by the thrust. In this derivation, we have assumed that the moment produced by thrust is not changing that much due to the small perturbation. That's why we are neglecting empty part. For the remaining part, for aerodynamic moment, we are assuming that it first of all it's a small angle approximation. So for a small angle approximation, we are moment is equal to dm by d alpha delta alpha plus dm by dq del q plus dm by d alpha dot into del alpha dot. If we put this equation in I by dq by dt equal to this, and by dividing I by y, we get three terms. First is m alpha, which is del m by del alpha upon I. Second is mq, which is 1 upon I del m by del q, and the similar is m alpha dot, which is 1 upon I del m by del alpha dot. The m alpha is act like a pitch stiffness, So it's like a simple spring moment. The second one is MQ, it's act like a damper, and the M alpha dot is the downwash lag. So what is the significance of the downwash lag? We'll see in a further explanation. So other equation we have taken is by using the second law of motion, that mv alpha dot minus q is equal to z alpha alpha. So how we'll come up with this equation, because it's not like aircraft has just only a pitch motion, it also have a up and down motion also. So capturing that thing, we are using a second equation where this term is acceleration term. Alpha dot is the how much my angle of attack changing, and the q is how much my pitch is changing. The z is called the variation in force in a z axis with respect to alpha, and just simply by alpha it means it is a dz quantity, so it's a force term here. So by simplifying by putting all this and become a state space representation, so we'll get this equation, and we know that this is the simply a into x term, and for solving this we are simply finding determinant of s minus ai equal to 0, and whatever determinant we get, we just compare with this characteristic equation of the second order auxiliary motion, where your omega n square is z mq over v minus m alpha. So the first quantity is relatively lower with respect to m alpha, so we can simplify it to minus m alpha. So as we can see from here that as my m alpha will increase, it is better to go change my omega n, and the second one is 2 zeta omega n is equal to minus mq m alpha dot plus z alpha by v. Here also the z alpha by v is very much small, so it's depend on this quantity only. So this quantity is a damping term, and this is the downwash lag. So what is the downwash lag? Downwash lag is that while the aircraft is pitched up, its wake will create a more wake, but it has some as the wake has to travel some finite distance. So in an initial time, if the pitch up is theta, so wake is generated, and here is my tail, but the wake has taken has to travel some L length, due to which the tail is still experiencing the older wake region, which is the weaker one. So the tail is creating a more lift, while when the wake is reaching that region, so it's automatically pitch up the aircraft, so it will don't have this much effect of the new wake created while the pitch up motion. The second one is the three graph is shown as per our formulation which is given by S square. If we find the roots of this equation, if my zeta is 0 to 1, so it's create a complex conjugate and a negative part of a negative real part. So it's mimicking this under depth condition where it slowly convert towards the stability. The second one is the zeta equal to 0, where you have a static stability part, but you don't have a dampening part. That's why it's just oscillating towards its neutral position. And the third one is zeta is less than 0. At that time, your whatever the aerodynamic dampening is there, it's not taking energy out of the system, but it's adding energy into the system. That's why the graph is diverging. Next is covered by Bharat.
Hello everyone. For a good dynamic stability, damping is very essential, and this damping ratio can decrease with altitude and Mach number increases. First, the velocity. The zeta is proportional to the inverse of velocity. Why? Because as the velocity increases at the higher Mach numbers, there is a more inertial loads on the aircraft. This will create more force to the oscillations, increasing the oscillations with higher amplitudes. But so the damping ratio gradually decreases with higher velocity, and the density, when at higher altitudes the density decreases. This creates the zero. It creates almost density approaching to the zero of the zero. So this will decrease the dynamic pressure of the aircraft. So for good damping ratio, the dynamic pressure is essential. As the consequently the dynamic pressure approaches zero, this will causes the both natural and aerodynamic frequency, aerodynamic damping to collapse entirely. And there are two phenomena which will affect the damping of the aircraft. One is the longitudinal vulnerability. This is because when the aircraft stalls, this will create a huge turbulent wake region behind the main wing of the aircraft, and this will go through the tail region. So the tail enters the wake of the stalled wing. This will create the local dynamic pressure to drop at the tail of the aircraft. Because for a proper damping, the tail is used to create the damping of aircraft, so to reduce the oscillations in longitudinal axis, and this can create locking the aircraft into a fatal deep stall. And another phenomena is observed in planes without the vertical stabilizer, because there is a directional damping which is primarily given by the vertical stabilizer. And when there is no this vertical stabilizer, it is more vulnerable to these directional oscillations. To overcome this, these kind of flying wings have to use some synthetic directional damping using the split drag rudders. These are special extra devices used in this kind of aircraft to create the damping to reduce the oscillations in lateral directions. Next, Gaurav will continue.
So here I'll be talking about lateral damping. So when an aircraft rolls, so what happens? One wing goes in upward direction, another wing goes in downward direction. So the wing which is going in downward direction, so there will be a vertical upward free stream component. So because of that, angle of attack will increase and lift will increase. So another wing which is going in upward direction, so there will be a vertical free stream component which is acting in downward direction with respect to the wing. So because of that, the angle of attack will decrease and lift will decrease. So because of the differential lift, what will happen? The aircraft will generate a restoring roll movement. So which actually comes naturally from the aircraft. So this is known as lateral damping. So what happens when an aircraft is having very high aspect ratio wing? So because of high aspect ratio, the wing is having very large movement arm. So because of that, the restoring roll movement will be very high. So the aircraft will be having very high damping. So the aircraft will be very highly stable. So next, aircraft has another damping known as cross-coupled damping or the Dutch roll. So when lateral dynamics and directional dynamics are coupled, then the oscillation is known as Dutch roll. So what happens because of side slip velocity? So the vertical tail of the aircraft produces the restoring yaw moment, and also because of the side slip velocity, if the aircraft is stable in roll, so it will create a restoring roll moment. So if the directional stability is weak compared to the roll stability, so what will happen? So the roll will create a side slip angle in opposite direction. So because directional stability is weak compared to the roll stability, so the aircraft will continue to oscillate. So this is known as Dutch roll. So which is shown in that video. And so to overcome that, the aircraft has to increase the directional stability. So to increase the directional stability, the momentum has to be increased, or the area of that vertical tail has to be increased. So if we increase the momentum, so we have to add some weights. So this is not good for the aircraft. And to increase the area of the vertical tail, so what will happen? So it will create an additional rolling moment. So this will also create the oscillation. So aircraft cannot be damped. So to overcome that, so aircraft has to add an additional yaw damper. So which is actually carried out through the deflection of the rudder. So, and next, I'll be talking about the during re-entry. So, the spacecraft or hypersonic vehicle, what happens at that altitude, the density is very low. So, because of low density, so the spacecraft is not able to produce aerodynamic forces. So, it's not able to produce damping by its own. So, what happens? The spacecraft should have stability augmentation system. So, it actually uses gyros to sense the pitching rate, yaw rate, or roll rate, and from that it will create restoring rolling movements accordingly. So this is how actually spacecraft generates damping. And next, Shubham will continue.
So from here on, we come to the part of parameter estimation. So the actual flight telemetry data is not very neat. We can see we can see a lot of noise in the data. So to estimate the parameters, we use a statistical method called utilizing maximum likelihood estimation, and that is used to extract the dynamic derivatives. And next, on the right hand side of the slide, you can see the computational aero. This is for to show the limitations of the linear aerodynamics. Actually, in the computational aero, we use the time accurate unsteady Reynolds averaged Navier-Stokes simulations to capture the non-linear hysteresis loop. Okay. And next comes the Mach paradox. Here, if you can see what happens when we suppose a car is moving at 100 kilometers per hour and we stick our hand outside, then the motion of our hand is highly resisted by the air. So why does we can see that at high speeds, why does the aircraft becomes unstable? So this is because there are two components in the aircraft, that is the damping. The damping ratio is actually has two factors, that is the aerodynamic spring, that is MQ, and the aerodynamic damping. So the factor aerodynamic spring is directly proportional to V square, and the damper is directly proportional to V. So the aerodynamic spring factor actually dominates at higher speeds. So the zeta is actually underdamped, leading to the instability at much faster speeds. And next, Soumik will continue from there.
Hello everyone. So dynamic stability generally relies on damping to make the oscillations be in control. And the air acts as a shock absorber and providing the damping. But here we'll be speaking about cases where air does not act as damping, but in that flow regime, it actually powers the oscillations more in place of damping. So in one of the curveballs was mentioned by Shubham, and now here we have the phantom downwash. So the question here comes, explain Cm alpha dot using without using any math. Why does the rate of change of alpha matter? So the thing is, generally the wing have a downwash behind, and when the wing pitches up suddenly, the air immediately behind the wing becomes has a greater downwash, but the horizontal tail senses it little later. This is because it is physically and geometrically placed way behind. As a result, there is a force mismatch between the wing and the tail, and this in cases where the force mismatch can they can resonate and not resonate, they can amplify the oscillations and can make it more dynamically unstable. And in the second case, we have the auto rotation trap. In this case, the question here comes, what happens to your roll damping derivative CLP if the aircraft is rolled while exactly at the stall angle of attack? At the stall angle of attack, the dynamics and the flow regimes is such. Here, generally what happens when when stick is moved, the damping stops the rolling of the aircraft immediately. But in the case when the angle is the stall angle of attack, here the wing going upwards faces a smaller angle of attack, and the wing that is going downward faces a larger angle of attack, and hence they are even more stalled. As a result, the rotation it automatically goes into rotation, and it is a very problematic situation to come back from that. And moving on to Nirav.
Good afternoon, all. Myself, Nirav. So, yeah, as we have seen throughout our presentation, let's close the loop finally on the X15 flight, which we have started on the very first slide. So, we have seen that flight didn't fail because of the integrity of the airframe, or it was because the airframe was unstable? No, that was not the reason. It was doomed by the environment itself, and let me explain you how. So throughout this presentation we have kind of used this analogy: spring, which is proportional to rho v square, damper, which is proportional to rho v, and mass or inertia, or let's say in our case it's the aircraft itself. So what happens at very high altitude and very high speeds? So we have already seen what happens at high speeds is that both these forces increase as the velocity increases, but since the static stability component increases with v square, the damping force is very less in comparison to static stability component, which leads to a overshooting phenomena in which the amplitudes oscillate and grow further and further, which leads to catastrophic failures. And what happens at high altitudes? Well, at high altitudes, the aerodynamic forces are negligible. As rho decreases, these forces, both these forces decreases. But we know that our mass is constant, so the inertia which our aircraft carries, it's still constant at low atmosphere, whether it will be low, whether it will be high atmosphere, or inertia is the constant. Basically, our inertia is same. So what happens is these forces are not enough to keep it in the loop when the aircraft reaches at very high altitudes. So it tends to destabilize and it cannot maintain the dynamic stability any longer. So why this happens? Because our flight is pretty much dominated by the physics of the environment, or let's say the physics of the problem itself. So the problem we have to encounter here is we have to get an engineer solution, or let's say we have to engineer a solution to a physics problem where we cannot use the physics of environment anymore, because the environment doesn't support flying at high altitudes. But that doesn't mean that we have to stop flying at high altitudes. We need to introduce some control mechanisms or some control loops which through we can synthesize artificial dynamic stability by which we can continue flying at such high altitudes, and fortunately we don't have to ever see such failures like that in the near future. Thank you very much. That was it.
You can come to the stage. Adarsh, you are mentioning something related to the behavior of damping with respect to the altitude through density and the velocity as well, right? And also zeta factor.
Oh, I didn't mention.
Who?
Sir, I mentioned, Bharat has also mentioned. So.
Okay. So essentially, if you're looking at it through purely the dynamic pressure alone, both rho and v have a similar kind of an effect. Though one, of course, is square, the other is different. But of course, altitude again, density, how it depends on altitude, that comes into picture as well. But you also mentioned the zeta factor.
Yeah.
Right. So the effect of dynamic pressure on damping and the effect of zeta on damping, are these contradictory, and how does that reflect on the dependence of the damping on the velocity? Some of the things came across in both of your slides and also the way you mentioned, but the conclusion was not very clear.
Okay, so as a perspective of only an atmosphere, so we are mimicking the similar type of configuration like spring and damper. So for both, if we have a lower density but still have a higher velocity, but the density is such that 0.00 something, that's why the both term is vanishes. And if we mimicking the similar way, but if we including the only the zeta factor, so as we already mentioned that the zeta factor is mentioning both mq and m alpha dot. So mq is already the damping part here, which is already mimicking with this 1/2 rho v square. So at a higher altitude, the mq will lower down because it doesn't have that much rho available, or in the second case where it's still in an atmosphere, but compared to the m alpha quantity, the mq quantity is such a smaller that the zeta will have a lower value. That's why the damping is lower. So in both way we can calculate, and we have to incorporate for a both way. If we know that my flight regime is in this month, so we have to also see that how much density is also changing with my mq and m alpha. And the same way, if my flight regime is let's say in an atmosphere, then how the density is still constant in a cruise flight, but my velocity is we can change velocity. So we have to encounter in both the things in our design itself, and then we have to come up with the whole flight envelope for the pilot or in a training module.
Want to add something?
What?
So another thing that you mentioned was in terms of the various stability derivatives. Okay?
Yes.
So if you look at just the longitudinal derivatives, two of the things that came into prominence in many of your slides was, any of you can answer. So two of the things which came into prominence was CMQ and CM alpha dot. Okay. Now
Yes.
Q is the pitch and pitch rate,
Yeah.
and essentially alpha dot is the angle of attack change with respect to time. In both cases, it's a derivative of the pitching moment coefficient with respect to that.
Yeah.
How does either of them differ? What is the paradox in terms of having two different quantities here? How they differ from each other?
So for CMQ, it's telling that it's just a del Q by del alpha. So how my pitch is varying with respect to my alpha. So it is just like del theta dot by del t, but where the del m by del alpha dot is telling that while changing my angle of attack, due to which the downwards phenomena occur.
Probably you didn't understand. Can you just write down
Yeah.
those two, CM alpha dot and CMQ? CM subscript alpha dot, and another one is CMQ.
Yeah. And
CMQ.
yeah.
So both are pitching moments, taking
Yes.
the derivative in one
Yeah.
case with respect to rate of change of angle of attack, the
Attack
other
and
case with respect to the pitch rate.
Yes. So both have a similar. They are detecting the same thing, but how it will differ from that? The DQ is just telling that how my pitch rate is with respect to my angle of attack, but here it's the alpha dot. So we are mimicking that how my moment is changing with respect to how much alpha dot is changing. So while doing this, if I just take one wing and one tail, so this part contribute is how my wing is contributing, how my tail is contributing, how my fuselage is contributing. But while seeing this m alpha dot phenomena, it's telling that while my wing is changing with respect to alpha, so it's dl alpha by dt, how much is changing, due to which how much lag is created towards the tail, due to which it will restore. It will restore the moment or not. We can see from this m alpha dot parameter. If it doesn't have a tail, so m alpha dot is simply a 0. So as we know that if we let's say take a B2 bomber or anything where there doesn't have a anything like a tail, so they are using aileron. They are using, so by flight controller itself, at the end of the wing they have a elevator, and they deflect such a way that they're mimicking the similar m alpha dot phenomena. So they doesn't have tail, so it doesn't mean that there is no we can't create a downward leg, so they are mimicking in this way if we doesn't have a tail.
Sir, actually, in case of CM alpha dot, here we are checking how the pitching moment is influenced by the rate of change of the angle of attack and how the air is influencing the pitching moment. But in the case of CMQ, we are generally checking how the pitching rate and the due to the pitching rate, how the airflow is being influenced around the aircraft and thus affecting the CM value, like pitching moment.
Correct. No, if you go to a little more fundamental level in terms of distinguishing between Q and alpha dot, then you will be able to answer this question better. Because the other aspect is the same. You are looking at CM, how it is changing with respect to either of these quantities. So the fundamental difference is between alpha dot and Q.
Yes.
Okay. Both are related to the plane of symmetry.
Pitching rate,
Certain
like
angle changes in the plane of symmetry with respect to time. Okay. But what distinguishes those two? That will then have an effect on how the damping changes.
So alpha dot is related to the wing, while the Q dot is related to the whole
Aircraft dynamics.
Because the pitching moment is itself defined for aircraft, which
like
combines
how much we are.
Yeah.
It's like any body, general body, we can have, like, say this is my nose and this is the velocity vector. I can have one is alpha, like if you decouple alpha dot and Q, one is if you have no Q component, that means body is not rotating but only velocity is rotating. So you have an alpha dot, and the damping which is caused due to the just velocity rotation, body being same, that will be coming from the alpha dot term. But if say alpha is same but you have Q, so it's like velocity is falling and you are tracking the velocity, so it's like this. That term, that damping will be from CMQ. So it's like two different things, and when you add, one is due rotation and one is due to velocity rotation. Added will come like
In case of alpha dot, there is an effect of air, like the flow velocity directions. But in case of the CMQ, we have the damping from the dynamics and the mass of the aircraft.
alpha dot is related to the rotation of the wing, while the Q dot is related to the rotation of the whole aircraft, whether pitch up or pitch down. It is related to the aircraft orientation or aircraft attitude, while alpha dot is related only to the wing attitude or let's say wing rotation. For example, if you want to maintain a steady level,
If it's the wing is fixed on the aircraft, then it's related to each other, right?
yeah, then they have to be related.
Most cases it is, yeah. Her explanation was right. So essentially, we are trying to take into account the velocity vector also. So these two are two different damping contributions that are there. Okay, so I mean, many of the conclusions were fine, but I think you have to understand the logic or reasoning a little better. So then I think things will flow. Adarsh, can you go to your slide of the things? Yeah, that next one. Yeah. So I think there are too many errors in this. Just take a look. Anybody even with a very basic background will see that there are lots of issues with this. Okay. So just don't please take anything blindly from the AI outputs. You have to look at it a little more carefully. Just I will give you one example. If you take a look at the first line in the table, rigid body and fail set because of aeroelastic deformation. The idea of aeroelastic deformation is when you don't have a rigid body. It's elastic. It has to be elastic. It has to be a deformable body. So these two are kind of contradictory, right?
But sir, in rigid body, we assume that center of mass CG position don't change, but due to aeroelastic deformation, it may change.
Yeah.
That's when this simplification fails, right, sir?
Okay, no, there are a few more issues. We just take a look at that and try to. You have not yet submitted a report on this, so maybe when you submit your part of the report, you can try to take a look at this and try to address some of those questions there. Yeah. Thank you. Yeah. So I'm just showing this only as a sample example, and this is something that is prevalent in many other slides as well. Okay, lots of issues with the outputs of the AI. I mean, many of the things are very useful and pinpointed in terms of what we want. So that way it's beautiful and very useful. But at the same time, you have to spend a little more time looking at the output to remove certain things which are not so accurate. Okay, so just try to do that. If you have any doubts, we can discuss later. Thank you. Anybody else had any questions for this?
Close नहीं होगा. Slip. Okay, sir. Ready? Good afternoon, sir. This is Team garuḍā, myself Abhishek Misra. Today we are going to present how effect of tail and control surfaces, how it will affect the dynamic stability of aircraft. As we all know, sir, that for stability there are two components. One is static stability, that just shows whether there is restorative force there or not once it is disturbed. Okay. So, and dynamic stability tells how this restoring force develops with time and how it affects the final equilibrium position. So, if roughly I will make an aircraft, say from a level flight, if it is disturbed, say I am considering pitching moment, but it will be equally valid in case of yaw and roll. Okay, so say if it is disturbed from this position to this position, now the restorative force will try to bring it to the level flight, but we all know because of heavy inertia it will not go and stop here, which is our ideal position. So it will just cross this or overshoot this, and again there will be a tendency to bring it in this equilibrium line, and like this it will keep on oscillating towards the equilibrium line. Now this oscillation may be a constant, in which case it will never come to equilibrium, or it may dampen, in which it will come to equilibrium, or it may grow with time, in which it's gone, means it's a disastrous failure. Okay, so the tail and control surfaces, okay, will act as a damper, which we know that if there is some damper, this will kill that oscillation and tries to bring it in the equilibrium condition. So this is the main outline of what tail and control surfaces will try to do or try to contribute towards the dynamic stability of the aircraft. Okay, and as we all know, this will be applied, tail on control surfaces will apply for forces or moments to the aircraft. For that we need to go through three fundamental concepts. One is moment arm of the vehicle, and second is how much is pitching angle change. Subsequent there will be definition of how yaw angle change also will be there, and roll angle change also. And third concept which we need to introduce is how much is that stable aerodynamic effectiveness of tail. Okay, that effectiveness is nothing but how much area of tail, which could be horizontal surface or vertical surface for respectively of pitch and yaw, upon how much is wing area and its chord length. Okay, further will be discussed by my teammates.
Good afternoon all. My name is Nitin.
As it has already been explained that the instabilities in the aircraft are seen as oscillations. So now I'll be focusing mainly on the how these oscillations will be dampened by means of the horizontal tail, and other aspects will be discussed by my teammates. So in case of longitudinal instabilities, there are two types of oscillations that the aircraft sees. One is a short period oscillation, which are of high frequency, and one is phugoid oscillations, which are of low frequencies. So in terms of short period oscillations, the objective is to dampen the oscillations as soon as possible, which is basically achieved by means of the inertia of the aircraft, where the presence of the tail, the horizontal tail, introduces pitch stiffness as well as pitch damping, which tends to dampen out these oscillations as soon as possible. Second is phugoid oscillations, which are low frequency oscillations, which basically happens because of the motion of the aircraft at different altitudes, which causes a change in energy or the exchange in energy between the potential energy and the kinetic energy. And that is basically linked to the drag that the aircraft sees, because these kinds of maneuvers basically happens at constant angle of attack. So more will be the drag, more will be the damping seen by the aircraft, and that is how the instabilities are removed. Further, the effect of the roll instabilities and the yaw instabilities will be discussed by my colleagues.
Okay, I'm Kaustubh, and so my topic will be a weathercock effect and about the directional stability that we see in a dynamic, in the terms of dynamic stability. So in an aircraft, if we face any slight slip, what do we want? We want to restore. So we technically want our CNB to be greater than 0. What does it mean? If you have a certain angle beta, which is your angle or directional angle, you just want a moment that restore itself. So CNB into beta, so the moment should be proportional to beta, and we should get a restoring moment. But this restoring moment come at a cost, and we always discuss that if you have more stability, we have less maneuverability, and that's the same thing. And the problem with the stability of a tail is it's not always the more stable, the more better, because there is some sort of exchange that we see between the lateral stability as well as the directional stability. And if one stability is greater than the other, we see an instability, which is quite counterintuitive. And what happens is if we increase our tail, or if we increase the volume or the area of our tail, the speed at which it comes back, it gradually increase. So we have a faster rate of coming back. Now there is something when your aircraft, today we don't have aircraft, let's use a duster. Okay, so if we have an aircraft and if it's pitching, we generally see that one of its wing is traveling more distance than the other, which means one of it has more velocity than the other, which means one has more lift than the other. So it's whenever you have certain yaw, you also have certain roll. The problem happens when one of the lateral stability or directional stability is more than the other. So suppose if your aircraft is turning and you have more lateral stability, what will happen? Your aircraft will come back, but your yaw is still there. So because of that, this one wing is producing more lift than the other, and you have a counter roll in the other direction. And if in an ideal plane, this should be in the same direction. So there is an out of phase thing between your lateral stability as well as the directional stability, and that what gives us a Dutch roll, when your directional stability and your overpowers its damping nature, and it's rhythmic and it's oscillatory. But something else is not oscillatory, that's your spiral mode. In most cases you won't even notice it because your aircraft is not oscillating. So what happens in this case, your directional stability is much more than your lateral stability. So even if your aircraft is turned, your plane will come into its natural direction, and in order to counteract, because you need some sort of your roll will try to balance it, and you will have more rolling. So after a particular point, your banking will just keep on increasing, and your radius of curvature will keep on decreasing, and you will be facing a larger and larger curvature, and that when you will have a spiral mode. In order to deal with this, we generally use our control surfaces or the stabilities or the control systems that we have in an aircraft, and there is certain maneuvering pilot use, And also this can be derived using an eigenvalues and all that stuff. But again, as we said, we are less prepared. I'm not going to comment on that. Next topic, I'll ask Ashish sir to explain it.
Good afternoon, everyone. Ashish here. So I will be discussing about the formula for this is the formula for the pitch damping derivative, CMQ. So as you can see, the formula entails it is equal to -2 of eta, which is the tail efficiency factor. Tail efficiency factor is nothing but the dynamic pressure at the tail to the dynamic pressure, the free stream dynamic pressure. And usually this will be less than 1 because the air flowing past the wing definitely will be having less kinetic energy as compared to the free stream. VH is our horizontal tail volume ratio, so it is given as SH LH by SC, where SH is the planform area for the horizontal tail. LH is the moment arm. This moment arm is from the aerodynamic center of the horizontal tail to the CG. C is our mean aerodynamic chord, and A1, or which we call as CL alpha, is basically CL alpha T, which is the lift coefficient for the tail. So now one interesting thing that we will note here, as I mentioned, VH is equal to SH LH by SC. So there will be two LH terms here, making the equation being proportional to the square of the LH. Kindly ignore this, it is mentioned as exponential. It is not exponential, but yeah, definitely when the tail length increases, the damping derivative, the pitch damping derivative increases square of the LH. And now we have the formula for the yaw damping derivative. So yaw damping derivative is nothing but similarly the way we obtain the formula for the pitch damping derivative, the yaw damping derivative is also obtained in a similar fashion, and in that it will contain the terms LV or LF, which is nothing but the center distance from the aerodynamic center of the vertical tail to the center of gravity. B is our wingspan, main wing wingspan, and VV, just like there it was the horizontal tail volume, here it will be the vertical tail volume, which will be again just like earlier way, it will be SF LF by SB. Here instead of the mean aerodynamic chord which was coming there, it will be the wingspan, because this is for the lateral stability. And your CL alpha V is the lift coefficient for the vertical tail change in angle of attack. Now my friend Shri will tell about Rohan will tell about control surface effectiveness.
Hello, my name is Rohan. Now, each and every one of us knows that how the aircraft is controlled. Basically, we use control surface to control the aircraft. By what does control surface do is change the camber and then does the aerodynamic forces on it. So here we are taking a tail, horizontal tail, and elevator. So what happens is that as the deflection is there, the camber is changed and the lift is increased. So here what actually happens is that, let's see how is CL. It is CL alpha tail into alpha tail plus CL del E into del E. This is basically the contribution of angle of attack and tail, and this is basically due to the deflection. So what happens is, let's say, and this is sometimes also known as elevator effectiveness. So let's say we have, this is high. So what does it mean? Actually, it means is that for small input, small elevator input, there are high tail forces. So also high pitching moment. So due to this, there is a faster correction of the disturbance. So if we want to achieve have better damping control, we have to have this high. So, but now let's look at something. First of all, I would like to make a correction that the above image, the lift direction should be downwards. So now let's take this case. What actually happens in rigid case and the flexibility case. Now let's say the elevator is deflected upward. What happens is that the lift is produced in downward direction. Let's say the changes lift is delta L due to the deflection. But now if it was the rigid, then it should have been the case. But then actually what happens is that it is a flexible.
So due to this, the drag also changes and there is a clockwise movement. So what happens is that due to this, there is a twist in the structure airfoil. So it's something like this. Let's say. So what happens is that we can see that the angle of attack is also increased. So due to this, there is also some delta L here. That's a delta L2. So what happens is that due to this, the control effectiveness decreases of the elevator. And sometimes, let's say if this delta L is more than that, so we can say, we call it a control reversal. So it also sometimes destabilizes the aircraft. Yeah, now I would like to call Kumar.
Thank you, Rohan. So now I will explain about the T-tail and deep stall. So as you can see, when the aircraft is at high angle of attack, it produces a separated flow and a turbulent wake region behind the wing, and it will expand over the T-tail configuration. So there is a loss of dynamic pressure near the T-tail because there is a highly disturbed flow near the horizontal stabilizer. So from the dynamic stability point of view, so due to the loss in tail effectiveness, there reduces the pitch damping and pitch restoring movements. To recover the aircraft from the stall, it is very difficult, and in some cases it is really impossible for that. So we can also say that this is zero control authority case shown in the figure. So that's it. Now, Sri.
So till now we looked into the conventional configurations of tail and how they affect on the dynamic stability characteristics of the aircraft. Now let us look into the unconventional configurations such as V-tail and twin tail. So since you already know, conventional configuration of tail has a two horizontal surface and a vertical surface, which is you can see in the normal commercial aircrafts. But the problem with them is they are like very simple, yet they have high interference drag, and because of this, your range characteristics will reduce. And one more thing is, if you want to make the aircraft stealthier, the vertical tail, which has if you have a vertical surface, the radar will be reflected exactly to the emitting source, and stealth is compromised. So if your goal is to make a stealthier aircraft, so you have to change the geometry. So for that they came up with some kind of V-tail configuration, which can be seen in many unmanned aerial vehicles as well as fighter aircrafts, the newer generation fighter aircraft, which has V vertical tails. So now let us look at the consequence of having V vertical tail on the dynamic stability characteristics. The problem is since already explained by the previous group. So CM, if you look at CM, it has many components: CM naught, CMQ, and CM delta E, all the derivatives. So as you know, as you have a V tail, the effective horizontal surface area SH effective is less compared to the conventional configuration. So this reduces the damping characteristic of the horizontal tail compared to the conventional configuration. So this kind of V-tail will reduce your dynamic stability characteristics, or let's say damping. So if the aircraft goes into, let's say, phugoid mode, the time after which it comes to its original position might be higher. The phugoid mode oscillation will take longer time to damp. Even the short period might take longer time to damp. So that's the character. Even the vertical tail effectiveness also reduces. But the thing is, as all of us know, design is a trade-off. It's never one hand higher or lower. You have to do trade-offs to get your desired configuration. So this kind of configuration, if you have seen, will be majorly used in unmanned aerial vehicle, which fly slow and they are lightweight. So the safety is not of paramount importance compared to the commercial aircraft. So that is one thing, and they are seen in fighter jet aircraft also, because they have advanced controls and high control surface effectiveness, and they have thrust augmentation also to account for this reduction in yaw damping or pitch damping. So coming to the twin vertical tail configuration, so if this is majorly seen in fighter aircraft, because fighter aircraft wants to have a high maneuverability. They are called some of the configurations which some of the aircraft which are twin tail configuration are Sukhoi 30, F-15. They are called super maneuverable aircraft. They want to perform high angle of attack maneuvers. If you perform high angle of attack maneuvers, there will be very strong wingtip vortices produced. And if you have a single vertical tail, this vortices will affect the performance of the vertical. This vortex will affect the performance of the vertical tail, which might reduce the effectiveness, as well as it might go into stall, which will not have any control. So when So to mitigate this problem, they use two vertical tails. So the effective vertical surface area is very high. So when you perform high angle of attack maneuver, you still have enough control power to come out of that maneuver. Because if you have seen Top Gun, everyone might have seen Top Gun. They show the Cobra maneuver, Pugacho Bell maneuver. They require high control power to perform that maneuver, and even the fighter aircraft perform flat spin maneuver. It's a falling leaf. So it's a controlled spiral. So that is only possible because of the big vertical tails and rudders, which give higher control power as well as higher damping, so that you can perform controlled maneuvers. Now coming to an extreme configuration, which is no vertical tails and no horizontal tails. What will happen? We have seen all these derivatives or contribution from the horizontal and vertical tail, but in this configuration we don't have any contributions. Now what will you do? How will you like make the aircraft stable and make the damping? If there is a damping, how will you damp the damping? So if you look at this configuration, they basically for the longitudinal control they use the reflex airfoil, which has almost Cm naught is equals to 0. The pitching moment is actually 0. So they have developed airfoils which have what do you say? Pitching moment is very less, so the control is also less required, and they place the CG in such a way that they somehow get marginal stability. So to avoid the damping or the going to unstable mode, they use a state-of-the-art control system, which was actually developed by the company which designed this, and through that they have this active control, which analyzes the aircraft for like let's say for a second it analyzes the aircraft's behavior 1,000 times and make necessary corrections. So for the yawing, they use a split. It's called split rudder, I guess. Yeah, they call drag rudders, which like open up and down, and they act like a vertical surface and create a non-symmetric force to rotate the aircraft. And even for roll control, they have split flaps where one flaps deployed at 20 degree and other flap is deployed at let's say 10 degree, and they produce asymmetric lift to control the roll. So this is how the newer configuration and the evolution in technology has enabled us to design these kind of aircraft. Thank you.
Sanket and Kunal finished. Sanket and
Kunal is absent, sir. Sanket is absent.
Yeah. Sanket is
absent. Yeah. I'm still absent.
I don't have anything. You have any questions? Anybody else? Any questions?
It was written, but there was something they called it more of a out of phase thing. Sorry, it was more of a out of phase thing that I studied it later, and it called ki it's mainly when lateral stability is more than the directional, you get the touch roll, and when the opposite happen, you get the spiral. But it's more of a out of phase thing. When the both of them go out of phase, you get a touch roll. In a directional stability, when it is more, it becomes more significant. So that's what I wanted to say, that if the directional stability is higher, the Dutch roll becomes significant, not that it vanishes. Yeah, yes, sir. It's yeah, as I said, the PPT it was written. Yeah, this actually it's it's overpowered by it should have been written like that.
So I think it was overall really good. This applies to the previous team also. As Najam was mentioning, this is a very difficult topic, and I think both of you have done reasonable justice based on the backgrounds. Thank you very much.
So in this context, I want you people to, I suggest you people to look into two terms. What is damping? Where is damping coming from? Think about it. I mean, will give you insights into the stiffer aircraft means where is that stiffness coming from? Don't have a spring anywhere. What do you mean by stiffness? As aircraft pitches up, instead of getting into this mode, it slowly comes back. So it is damped. Where does that come from? What is damping? How does aerodynamics gets into all this? It's very lucid, very sweet, and a very good topic. Just a matter of thinking. Damping and stiffness, both are the parameters. Give a thought to it. It would be nice if other presentations also come out with like puṣpak pioneers. If you can exhibit or come out with what is really the damping, where is the damping coming from? I mean, stiffness means stiff aircraft to control in terms of dynamics. Like how it will be a good learning to the class. No, I mean, no question, nothing, no comments, just a learning, just thought.
And the basic point to what he's trying to bring out is when you go to the fundamentals, understand a lot of these complicated things that you're talking about even better. It's very nice. Many of these are fancy names and case studies which are like really dramatic and nice to listen to. But try to get down a little bit to the physics. You may not need to go into great detail in terms of the mathematics, in terms of modeling, because as previous team also pointed out, there are a lot of assumptions involved. So it's not a very realistic model we have, but we're trying to gather all the major effects and try to see what is the thing. But at least qualitatively, we can understand once we go into these basic aspects, like what you was talking about from an aerodynamic damping point of view. Most of the time, we are dealing with in this course rigid body, but otherwise you have flexible body, you have the structural material damping that is coming into picture. Then, of course, you bring in all the dampers and the additional things that you're bringing in from a controls perspective. So, what is the relative orders of magnitude of these? Will vary, of course, from design to design and the specification, the requirements for the vehicle as such. But once you start going back to your first courses that you have gone through an undergrad in terms of the meaning of damping, and then you try to understand the bigger things in a much better perspective. Thank you. Let's try to finish all the backlogs on Monday so that we are on stream from Wednesday onwards. Okay. So even if some of you have issues like health issues or whatever the other things, travels or exams and things like that, ensure that the rest of the team shares the load and we can try to finish. An example is ArchAngel. They started with 4 members and 2 have dropped out and the other 2 are taking care of the load. I think the other teams can do it in a much better fashion with 5 to 9 member teams. I think you have just of an excuse. So far what has happened is fine, but I think going forward, let's try to finish things on time. Thank you.
This week's report.
Okay, sir. So our topic is little similar to them. They had like variation in CG. This is a variation in load, which is a cause of variation in CG, you can say. So variation in load load can be, cargo, or if you just deploy a payload or any sudden change in the configuration due to any inertia change or anything. So and fuel consumption. So that will also cause continuously change in load. So that would affect center of gravity and moment of inertia, and how that would affect the dynamic stability of aircraft. That is our topic, and that will be presenting. So most of the things already, like dynamic stability and lot of definitions, have been nicely covered in the previous groups. So as an end, we'll reuse that. Pragya will be presenting the definition.
So I'll just repeat whatever the previous presentation they have done already. So differences between static and dynamic stability. Static stability is the tendency of an object to return to its equilibrium position just after the disturbance. In dynamic stability, we notice the behavior along with time. Then there are three types: positive static stability, neutral, and negative. Same in dynamic stability case. So this is a pictorial representation. So just when this aircraft is slightly disturbed, it will return back to its original position. For positive static stability case, for neutral, it will, if it's disturbed, it will continue in that disturbed path, and for negative, it will, if it is disturbed, it will be continuously like ongoing that disturbance. For dynamic stability case, it will undergo some oscillations. So for positive case, it will be like when it is disturbed, it will continue for some oscillations and the amplitude will decrease with time. For neutral stability case, it will continue with the same amplitude. For negative stability, for negative dynamic stability, the amplitude will increase with time. Then load variation. So load variation is the change of total mass and mass distribution. That is mainly the change of center of gravity during the operation of the aircraft. So these are the causes of load variation. First, fuel burn. So whenever the aircraft is in flight, so the fuel from tanks or fuselage tanks or from wings, from engines, the total weight decreases. It causes the center of gravity to shift. Then passenger movement within the cabin, when the passengers move, the center again shifts. Cargo shift, if the cargo is not properly settled in the loading area, so that will also cause a change in moment of inertia of the aircraft. And payload release, so for military aircraft things, like whenever we are, what I would say, so for missiles or whatever things, this will also cause a change in mass distribution. Now I would like to call Bhavika for further discussion.
Thank you, Pragya. I, Bhavika, will be explaining the effect of center of gravity with the variation of loads. I think this topic has adequately taken by the previous group, so I'll be brushing up. So the center of gravity can shift forward or aft with respect to the neutral point of the aircraft. So we have the static margin equation, which is location of neutral point minus location of center of gravity by mean aerodynamic chord. So whenever the aircraft CG shifts forward, the aircraft becomes nose heavy, and it increases the nose down movement, which in return the tail needs to produce a larger downward force. So the aircraft becomes stable, but it also becomes sluggish. With the aft shift, the wing moment, which is the moment pitching moment, decreases. So the tail does not need to produce a large balancing force, but the aircraft becomes sensitive to the pitch. And if the CG goes beyond the neutral point, the instability occurs, which means it with a gust or a disturbance, it amplifies the disturbance instead of restoring the aircraft back to its position. This leads to a diverging motion. So with next, I'd like to pass on to Harika. Thank you.
So I'll explain about effects of moment of inertia. So I'll tell you what moment of inertia is. Moment of inertia is same as mass, like mass resists the translation motion, and moment of inertia resists the rotational motion, and which is expressed as I is equal to mr square. So it depends on the axis we consider. So for aircrafts, we consider CG axis in roll, pitch, and yaw. If the moment of inertia is high, like to control the aircraft, we apply some torque, which is equal to I alpha. So if we for controlling aircraft, if the moment of inertia of the aircraft is large, then the alpha would be small. So effect of the torque would be less to control it. So heavier the aircraft, the slower would be the response, and if the mass is less, I mean the inertia is less, then the oscillation would be quicker for the same amount of controlling. Pitch, so depends on how the roll pitch and your moment of inertias are, depends on the load, variation of loads. So if in the roll axis we consider, if the axis, so consider if fighter aircrafts, so if they have a load on the wings, depending on the location of the load on the wings, the moment of inertia in the roll changes. As of in the pitch axis, if the payload is location of the payload with respect to center of gravity axis, moment of inertia in pitch axis also changes, and also in yaw. Similarly, so and it also affects natural frequency of the aircraft. So if the load is closer to CG axis, that is moment of inertia is less, then it has tendency of higher natural frequency. Like frequency is there I have given root of k by m, where k is aerodynamic stiffness and m is inertia. So according to that, if the inertia is high, the frequency would be low and the response would be faster, that is quick response to disturbance, and same as if moment of inertia is higher, then the frequency would be lower and the oscillations would be slower, the response would be low. And there I have given an example of a short period response where it is the frequency is equal to root of minus m alpha by Iy, which is elaborated by Michael.
Good afternoon, everyone. So I'll be now talking about the longitudinal dynamic modes. So we have in the longitudinal dynamics, you have just two kinds of modes. One is the short period and the other is the long period. So if it look at the short period dynamics, it is effectively a second order equation in the variation in angle of attack. So using our standard second order equation, you can see what the frequency of oscillation and a damping would be. So as it is visible from these equations that the frequency and damping are themselves function of the moments, and moments are themselves functions of the velocity and the coefficient, and the coefficients also are the function of the alpha dot and the q and other states whichever are included in our dynamics. So we can see that as the state changes, the load will also change. That will change the dynamics because it changes the frequency and the damping. So the best effect of this is, as we can see, the m is of this form, the half rho v square sc cm. So we see that m is varying as v squared. So you can see that as the velocity increases, the omega will also increase with order of v, not v square. And similarly, zeta, the damping, also will increase as the order of v, because on the numerator we have v square and the denominator will have under root of v square. So v square by v, again order of v. So we can see the velocity will change both the omega and zeta, and also there will be some dependency on alpha dot and q as well. So this is as far as the short period is concerned. Then we'll come to long period. Again, so long period is the variation in the velocity and the flight path angle, and the others are assumed to be zero. So we have a 2 by 2 system here. So since this is a 2 by 2 system, we can use the characteristic equation to find the frequency and the damping, and which come out to be as given here. So the damping would actually, if we find it properly, it will be a very big equation. But if we can simplify it for a gamma not equal to 0, equilibrium gamma at level flight. So again, here we see that the omega of the fluid mode is actually dependent on the velocity square. So if the velocity is higher, the omega is actually lower. And we can say after simplification that the zeta is fairly constant, but in actuality it won't be. But then we can simplify, then obviously we can simplify it. And if we see inside, so the CD by CL, again, both of them are function. I mean, it's not drag, but both of them vary with the same kind of order. So the CD by CL would be order of 0.1, and it won't vary as such. But the main variation is on the V square, which is a very significant variation. So this is about the longitudinal dynamics. Now we'll have the lateral dynamics which will be taken up by Suru.
So I'll discuss on the effect on lateral directional stability. So because yaw and roll are inherently coupled, I've just written here is like the equation of motion. I mean the translation and rotation. So XYZ is the forces, capital XYZ is are the forces, and MV dot so in body frame. And then the other one is TT is the torque. So that acting, so that would be d by dt of L, which is dl by dt plus omega cross L. So what we can see is inertia is, so yeah, so if we see the rotational dynamics, that has I omega dot plus omega cross I omega. And if you have, so now it looks very populated term, but usually if, like the first class when we discussed, sir had told that we assume that there are plane of symmetries and we carry on with assumptions so that life is simpler. And most of the times if the loading is symmetric, a lot of assumption say y axis we can take a plane of symmetry, and then xy and yz I xy yz components will be off gone. So a lot of so if this is just diagonal term, there is no coupling between terms. But if there are off diagonal terms, they will couple each other. So each rate in one direction will affect the rate in another direction. So that is the thing. So yeah, so we would want axisymmetric load, but obviously we are presenting here, so we don't have axisymmetric load. Yeah, so there are three major lateral directional stability modes which you can see. So which is dependent on how the stability, like roll stability and yaw stability is with respect to each other. If one is very fast, one is very slow, we'll have one sort of response. So if roll is really strong, the stability is very strong, you'll have roll damping seen, very fast damped oscillation, that is roll damping. If both are very comparable, then you might get a Dutch roll if you get a disturbance in that sort. So because both will, so yeah, so I think already we don't, okay, yeah, I'll discuss. And then spiral is when it is opposite, that is yaw is very strong, but the roll stability is very weaker. So we'll have different modes. And how will load variation affect these is, it will change the moment of inertia, it will change the mass distribution, which already they told. And then, yeah, so it will create asymmetry, which is the cross-coupled terms, and which will cause the coupling between the different yaw and roll, since we are specifically talking about lateral stability. And so if we have an axisymmetric lateral load, say there were two payloads and we just dropped one missile from the left wing, and then there is right wing, it has missile, or some due to some reason, we'll have fully populated inertia tensor, and we'll have inertia tensor. So that will cause coupling. Now if there is a YCG change, which I told that something is dropped from right wing, or the CG is shifted due to any reason, so that will create a additional yaw moment. Now what we would want to do is, like we would trim accordingly. So we'll have a additional say we have a YCG, so it is like this, and then we have one weight here higher and lower here. So it will sort of bank because the weight has distributed. Now you would want to bank back, like you will want it to go to steady, and you will deploy ailerons. And accordingly, what will happen is you will have an unequal lift distribution in left and right wing. Now unequal lift distribution will cause unequal drag, which will cause yaw. So you are trying to match roll, and then you are causing yaw. So it's like, yeah, you are trying to catch up one, and then you are causing another. Now you'll have yaw, you will deploy rudder, and so it's a cascading effect. Yeah, so yeah, you need commands, and hence everything you do, it will be coupled. So if you have axisymmetry, you do roll, you will be coupled with yaw. You do yaw, you will be coupled with roll. So now for roll damping mode. So roll damping mode, as told, is a highly damped. When you have a very highly damped roll mode, the stability in roll mode is very high as compared to the yaw. And if we see the linearized dynamics, so I think Vaishnav, Navya had shown a bit of it. So yeah, if we just linearize about trim condition, we can get delta P dot, which will be coming from the, okay. So as delta P, so it's like perturbation, rate of change of perturbation is a factor, like something times perturbation. So this is the lambda term, like when we say e to the lambda Ta, so lambda comes in front. So if this is high or low or positive negative, that will make that perturbation is growing or not. So if you have a positive delta P, you would want this coefficient to be negative so that delta P dot is negative. And similarly, this can translate to delta Q, any sort of system. So you would want LP to be less than 0 for a stable system, and the time how it grows or decays will be determined by IXS by LP, the inverse of it. So if you have a high moment of inertia along roll, say you have distributed the mass such that, or your mass has varied such that you get higher inertia, you will get slower response. So that is how load variation will affect the roll damping mode. Because roll damping is simpler, where you just have a roll, roll mode. Then, so other two modes are Dutch roll and spiral mode. So Dutch roll, as I told, is when both modes, yaw and both stability, directional and roll stability are comparable. So there, I think this I need not discuss what is Dutch roll, because many times you have discussed already that. Okay, so it's like out of phase sort of. You go to you roll, but as soon as you roll, the yaw is such that you should be the yaw will take it again. Okay, so it's like simultaneously you are yawing and rolling. So it is a self-sustained oscillation. And now here also, if you see the beta dynamics, so beta r dot, and if you linearize, then we can, for linear system, when the perturbation is small, we can consider that r is equal to beta dot. Like delta beta dot is r. So we can put this here, and we'll get we'll get an equation in delta beta double dot, which we can where beta we can assume as e to the power lambda t, like we typically do for a homogeneous equation, and we'll get this sort of equation. So we can say this is the natural frequencies, and this is the zeta omega 2 zeta omega n term. So here also again we see that inertia comes in the denominator, and this is okay. So this obviously depends on the stability you have for yaw as well as the dihedral stability. So if the loading gets away from CG, or due to so then IZZ will increase, and then the response will be slower. So it will be like the damping also will be lower. So it will sustain for a longer time, and it will be a slower Dutch roll mode. Now for spiral mode, if we see spiral mode again, we have spiral mode is more on when you have a strong yaw but not enough roll. So if you see the so if you have if you write delta p, okay, so here p dot, if you should put the bit to mathematically. So if you do p dot 0, then you have a residual term delta p equal to delta r delta p. And if you so delta r delta b we can write from in terms of delta phi, and we'll get a equation in delta phi dot. So here also again, if you increase the moment of here also again we have IZZ in the denominator. So if you increase the moment of inertia, the spiral divergence will be slower, which is even further difficult to detect, because spiral divergence actually is a slow mode where pilot is not able to detect, and sometimes you just fall down and he'll think that you are losing lift, and you will trim up like pitch up sort of, and you will tighten the curve. So this will further worsen that situation. And if the loading is axisymmetric, there will be again another forcing term, because the weight will again initially I told that it will roll along the heavier wing, and which will even further tighten the spiral. So both ways it is worse. So if you increase the inertia, it will worsen the spiral mode, and if you have a axisymmetric loading, you would the spiral mode might go towards the heavier wing side. Yeah. So next is the practical implication, which will be covered by Bhavesh.
Good afternoon, everyone. My name is Bhagyashree, and till now we have seen a lot of theories. Let me talk about some practical implications of how variation in load can affect dynamic stability of an aircraft. So from the introduction slides, we have already seen that there are like fuel burn is one of the cause for variation in load. So from the anatomy of aircraft, we know that fuel tanks are usually stored in wings or fuselage in case of large aircrafts. So as the aircraft takes off and then continues to fly, fuel burn takes place, which reduces the aircraft total weight and also changes the distribution of mass, because the fuel is going and like from this figure we can see that if there are two tanks on either side of the wing, if one tank is having lesser mass than the other, it can cause an unbalance. And we have also seen that excess baggage, like because of the load, also the payload can also affect the CG change. So basically forward and what happens in practical cases is, for forward and aft CG limits are specified by the aircraft manufacturers in pilot's operating handbook and aircraft flight manual. And this maintaining the flight in that limit is very important, because it also results in adequate pitch control authority, which is basically the elevator and tail system's ability to control the pitch of the aircraft. And then pilots must also verify the CG position before takeoff and also sometimes for landing fuel conditions. So there are two charts that pilots come across while operating. First is this CG envelope and then this loading chart. So first, loading charts, it helps pilot determine the aircraft weight and CG before takeoff. So by determining these aircraft weight, moment on each load component and final CG location, the pilot verifies that it is well within the limit, so that the operation, like the flight is safe to operate. And from the CG envelope we can see there is this forward CG limit and aft CG limit. This is the maximum weight of the aircraft, which is also the maximum takeoff weight. And if the CG is lying within this envelope, it means the aircraft is safe to operate. And there is two more things we can see: normal category and utility category. So in this, basically normal category, the passenger aircrafts and all, it will fly under that limit. But if the aircrafts are slightly aerobatic or the aircraft has more maneuverability, it maintains this envelope. So that is all for practical implications of variation in load. To conclude this presentation, we have seen how load variation takes place in an aircraft, and then we have also seen how it affects the dynamic response, and we have seen the practical implications, that how the pilot should operate by keeping the limits within the aircraft manual limits mentioned. So that's all for this. Thank you.
Any questions?
Huh?
Any questions? No, you want to?
Yes, sir.
Good,
Apurva,
good.
I think he informed he is out of town.
Yeah. So, Maiko, while you're talking about the longitudinal dynamics, you had the equation for that. Yeah. So I asked a kind of similar question to one of the previous teams. So if you look at the second equation, the second term there.
Yes, sir.
Right. So in the coefficient, we have two things in the numerator.
Mhm.
One is how the pitching moment varies with respect to the rate of change of the angle of attack.
Yeah.
The other is how it changes with the pitch rate.
Yes.
So I want you to kind of distinguish this for me.
The pitch rate and the
Yeah.
rate of change of angle of attack.
Because think of you teaching a class and people get confused between these two, right? Between Q and alpha dot. Why should they be two different things?
So, okay, so the pitch rate is basically, I mean, if you see just the frames of reference, the body attachment and the inertial frame, the pitch rate is basically the variation of the theta, right? The theta which is from the inertia to the body, but the alpha is different from theta. And let's say this is the wind now, or okay, whatever. Let's say this is the wind, V infinity. The alpha is actually this angle. Right. So it is now it is also not necessary that the Q and the alpha dot are same. They can be different, right? Because I mean it's a dynamic thing. So basically, if the aircraft is doing like this, there might be a the theta will vary as the aircraft pitches, but the angle of attack might not vary as such, because if the aircraft is going like this, the theta itself is becoming like this, but the angle of attack is still like. But now since it's very high angle, so it's not valid within this regime because it's linearized. But this is essentially the difference. So the pitch rate is different, and the alpha dot is different.
Okay, good job. Between those two, which do you think will be a major contribution, or can't you say that in general?
The major
Between
contribution.
M alpha dot and MQ, which will be dominant, if at all?
Okay, so actually, even I am confused within it. I would assume that alpha dot. Sorry. I mean, yeah, I still think it should be M alpha dot, because that is what the aerodynamic thing is, right? So that is what actually dictates it. But the Q, I mean, I think Q wouldn't be that much, because it's a control thing, I think. I mean, I think we can neglect it also, I feel. But again, in my UG also, I didn't get an answer to this while I was in. So I'm also confused.
Okay. Yeah, so the topic for you was load distribution, right? So by load, you understood it to be the weight, essentially, right? But when you say load variation, it could be either the load distribution variation or the load itself varying.
Yeah.
Okay. So in other words, you could have a similar percentage of the distribution, but you could have the overall load reduced. So let's say the overall weight of the aircraft is less. Yeah. So that aspect didn't come out very clearly as to what effect it could have on the dynamic stability. Could you speculate on that? Because I saw a lot of information both for the longitudinal dynamics as well as lateral directional dynamics in terms of when the load distribution changes, how these things could change. Okay, and it was very good. But if the load overall weight itself changes, but CG is similar at a similar location because the overall load distribution is the same in terms of percentage wise. Right? So then how could that reflect on either of the stabilities?
Sir, so like you want to? No, so sir, so if you are saying in terms of you're saying the CG is same, but the weight distribution itself has been changed in the way that CG is same. So I mean, the total weight could either have increased or decreased, right? So based on that, the inertia would also change, right? Because it depends on how far the weight is from the CG. So the inertia could increase or decrease based on that. So again, it will affect the omega and the damping as well, because they come in the expression. Not here, but here, yes.
No, see, because once the load, the overall weight comes down, as he pointed out, so the moment arms will be same, but the weight itself comes down. So essentially, you're thinking of everything reducing in a particular way so that the CG doesn't move much. It's on, but the overall weight has come down. So in other words, without the CG shift, can just the change in overall weight, can it bring a difference in terms of the, I think he brought out...
whatever we discussed was for I only. Whatever we presented was for inertia change.
Correct.
That was weight is constant.
While I was speaking,
right.
While I was speaking, sir, my emphasis
So
was
I'm
more
asking
on
the other way
the
around.
movements. While I was speaking on this slide, my emphasis was more on the movements, because I thought I should more emphasize on the variation of the load, which are the movements here right now.
Yeah.
So I thought of emphasizing that.
Okay, no, I think you answered it quite well. That's fine. Thank you.
Okay.